Welcome to the Deep Dive. This is the show where we take incredibly specialized research, often straight from the source, and we really unpack it.
That's right. We don't just tell you what was discovered. We dig into the how, the why, and the intellectual journey behind it.
And today, our journey is taking us deep into a submitted manuscript from the world of combinatorial number theory and probability.
A really fascinating one. Our listener asks us to deconstruct this paper entirely, and I mean entirely, sentence by sentence.
So our mission today is a meticulous, linear, and extraordinarily deep dive into a Halász-type theorem for permutation anticoncentration.
And just to set the stage, this methodology means we have to slow way down. We're going to look at the foundations, explain why every term was chosen, every definition crafted. It's really an immersion into how a mathematical proof is built.
The central topic is anticoncentration. It's a simple idea, really. How spread out are the values of a random variable?
Right. And specifically, how spread out are sums that you get by randomly pairing up two sets of numbers. So let's start right at the top and unpack this title. ##I. Title, authors, and abstract. The hook and core claim.
Okay, so the title is a Halász-type theorem for permutation anticoncentration. Let's start with that first part. What makes a theorem Halász-type?
Halász, his work in the 70s was just a massive paradigm shift. Before him, people mostly used simple tools, like variance, to estimate how spread out a random sum was.
High variance means low concentration. Pretty straightforward.
Right. But Halász showed that for sums of independent random variables, the real story wasn't just variance. The amount of concentration is fundamentally controlled by the additive structure of the numbers you're summing.
Additive structure. What does that mean in this context?
It means looking for short additive relations. Things like, can you take a few of your numbers, add or subtract them, and get zero? If you can do that a lot, your set has a lot of structure.
I see. So lots of structure leads to high concentration. The sum clumps up. Little structure means it spreads out.
Exactly. So a Halász-type result, like this paper claims to be, is one that connects concentration bounds directly to some measure of the structural complexity of the input data.
Okay, that makes sense. So what about the second half, permutation anti-concentration?
Well, this defines the specific random model we're in, and it's a crucial distinction. The classical problem involves independent variables, like coin flips.
Right. You have a set of numbers, A, and you multiply each by an independent random 12.
Here, it's different. We have two sets of numbers, let's call them A and B. They're fixed. The only randomness comes from pairing them up. We take a random permutation, pi, and we form the sum of A times B pi.
So because there's only one permutation, the choices aren't independent at all. If B3 gets paired with A1, it can't be paired with A2.
Precisely. The terms are highly dependent. And that dependence makes this problem much harder than the classical setting. We're measuring how unlikely it is for this very specific kind of random sum to land on a single value.
Got it. And the authors tackling this are Zach Hunter, COSMIN POHOATA, and Daniel G. ZHU. The affiliations are ETH, Zurich, Emory University, and Princeton University, respectively. A really strong lineup.
Absolutely.
Okay, that covers the title and authors. Have we missed any nuances regarding what the title is signaling to us?
I think we've thoroughly unpacked the core concepts introduced there. We know it's about concentration, we know it's about structure, and we know it's in this harder dependent permutation model. Let's move to the abstract.
All right, the abstract. Sentence 1 lays out the setup. Given a set, A par A1, a half in real numbers and real coefficients, B1, AB, ABN, consider the distribution of the sum obtained by pairing the A's with the B's according to a uniformly random permutation.
Okay, so this is just formally stating the mathematical object we're studying. The random variable, let's call it y, is the permuted sum.
The expression type is the permuted sum.
The latex is y sum I add AA.
The phonetic is y equals the sum from I equals 1 to n of a sub I times b sub p of I. And why is this specific model so important to study? Where does it show up?
Well, it's a model of randomness that appears in places like random matrix theory, for one. And in complexity theory, it's a more constrained type of randomness than what you see in the classic Littlewood-Offord problem. Because the building blocks, the sets A and B, are fixed. Only the wiring between them is random.
Okay, so a different flavor of randomness. The next sentence introduces the baseline. A recent theorem of Pawlowski shows that as soon as the coefficients are not all equal, this distribution is always spread out at scale n to the minus 1. No single value can occur with probability larger than, and then there's a formula.
This is the benchmark they're trying to beat. The expression type is the maximum point mass bound from Pawlowski.
The latex is Fackel1 steel and 2 seal plus 1.
The phonetic is 1 divided by the quantity 2 times the ceiling of n over 2 plus 1.
So let's unpack that. That denominator is roughly n plus 1. So the whole thing is basically 1 over n.
Exactly. Pawlowski's result says that if your coefficients aren't all identical, the probability of hitting any single value can't be bigger than about 1 over n. That n to the minus 1 decay rate is the universal worst-case bound.
Got it. So the next sentence must be their core contribution. We show that stronger anti-concentration holds when the coefficients have additional diversity.
And there it is. The rhetorical purpose is crystal clear. We are going to beat Pawlowski's n to the minus 1 bound.
But how? The next sentence explains. We quantify the structure of the coefficient multiset by a simple statistic depending on its multiplicity profile, and prove that the maximum point mass of the permuted sum decays polynomially faster as this statistic grows.
This is the Halász type mechanism we talked about. They're introducing a new tool, a statistic, which we'll find out later is called MB. This statistic is designed to measure the diversity or structural complexity of the coefficients.
And the more complex B is, the faster the probability decays.
Right. And the final sentence of the abstract gives us the big payoff, the most dramatic case. In particular, when the coefficients are all distinct, we obtain a bound of n to the minus 5 halves plus little o of 1, which can be regarded as an analog of a classical theorem of Erdős and Moser.
Wow. Okay, let's look at that exponent. The expression type is the distinct coefficients bound.
The latex is n52 plus O1.
The phonetic is n to the power of minus 5 halves plus little o of 1.
This is where it's really, really interesting. Minus 5 halves is minus 2.5. That is a dramatically better decay rate than Pawlowski's minus 1.
It's a massive improvement. And they connect it to Erdős and Moser, which suggests, this is a deep foundational kind of result in this permutation setting.
Absolutely. The O1, the little o of 1 term that signals a slight loss, probably something logarithmic. We'll see that's a crucial detail later when they talk about future work. But the main story is that exponent, minus 5 halves.
Okay, that covers the entire abstract. We've established the Pawlowski baseline of n to the minus 1, the introduction of this new diversity statistic MB, and the really impressive final bound for the distinct coefficient case. Have we missed any nuances here?
I think we've thoroughly unpacked it. We've highlighted the key players. Pawlowski's result as the floor, the need for a new way to measure diversity, and the target n to the minus 5 halves decay. Let's proceed to the introduction, which starts with a really nice geometrical interpretation.
Right. The first paragraph of the introduction recasts this whole problem in geometric terms. It starts, let A equals A1, n is a set of n real numbers, and let S be the set of points, epi, MB, where pi ranges over all permutations of n, 1 to n.
So we're not thinking about a sum anymore. We're thinking about a collection of points in n-dimensional space. On R and n, there are n factorial of them, and they're all generated by just shuffling the coordinates of a single starting vector, A1, n.
And these points form the vertices of a geometric object called a permutohedron.
That's right. And then they ask the core question in this geometric language. What is the maximum number of points in S that lie in a hyperplane?
Okay, let's do a quick digression on hyperplanes. What are we talking about here?
A hyperplane H in n-dimensional space is just the set of points that satisfy a single linear equation. So an equation of the form b1 by 1 plus bi plus bnxn equals c. The bis define the tilt of the plane, and c defines its position.
I see. So the question, how many permuted points lie on the hyperplane, is the exact same question as, for give n a set of coefficients b and a target value c, how many permutations pi make the sum equal to c?
Precisely. It's a perfect equivalence. The probability question is a geometry question.
The paper then points out a trivial case. As stated, this question is trivial as every point in S lies in H0, which is a specific hyperplane.
Yes, the trivial hyperplane. The expression type is the trivial hyperplane Hn.
The latex is H0 by 1, mid by 1 plus each dots plus xn encoded in A.
And the phonetic is the hyperplane H0 is the set of vectors x1 through xn in Rn, such that the sum of x1 through xn equals the sum overall, A in A of A.
So why is this one trivial?
Well, the equation for this hyperplane is just by 1 plus xn equals a constant. But if your points are just permutations of the same set of coordinates, the sum of the coordinates is always the same. Doesn't matter what order they're in.
Ah, right. So all n factorial of the points already lie on this one specific hyperplane, so that question isn't interesting.
Exactly. So the real question is about any other hyperplane. And that's what Pulaski answered. If we exclude A0, this question was recently answered by Pulaski, who showed that the maximum number of points in S lying on a non-A0 hyperplane is n1 if n is odd and nn2 if n is even.
Okay, those are specific numbers, but what's the takeaway?
The takeaway is that these numbers correspond to a fraction of about 1n of the total n factorial points. This is the geometric version of his n to the minus 1 probability bound. He showed that the maximum number of points you can get to line up is achieved when the coefficients defining the hyperplane are very, very simple.
And this result had some concrete applications. In the case A equals n, this result can be interpreted as bounding the maximum number of vertices of a permutohedron that can lie on a hyperplane, answering a question of Hegedus and Caroly.
Right, so this connects the more abstract probability problem back to a very concrete question about a specific geometric object. It shows why people in geometry care about this.
The paragraph closes by noting some extensions. Recently, Kong and Zheng proved a similar result over the complex numbers, which in turn extends to all characteristic zero fields.
Which just shows this is an active area of research. The core geometric idea is robust.
Okay, that covers the first paragraph of the introduction. We've set up the geometric context and seen Kalowski's result about the maximum number of permuted points on a non-trivial hyperplane. Have we missed any nuances here?
I think we've thoroughly unpacked it. The crucial connection for you to hold on to is that the probability question about anti-concentration is exactly equivalent to the geometric question about hyperplane containment. The coefficients by just define the plane. Let's go to the next paragraph.
The second paragraph is where they really motivate their own research. It starts, a close examination of Pulaski shows that for n greater than or equal to 8, the only hyperplanes achieving equality in the above bound are of the form b1 by 1 plus being xn are the same, where at least n-2 of the bi are the same.
This is the key insight. The absolute worst case, the case with the highest possible concentration, only happens when the coefficients defining the hyperplane, the b's, are almost all identical.
In other words, when they have very low diversity.
Exactly. So the next sentence draws the logical conclusion. Combined with the fact that H0 contains all of S, this suggests that as the bi become more diverse, it should be possible to prove stronger upper bounds on the number of points in S lying on the hyperplane.
Right, there's an implicit therefore in there. The authors are basically arguing that Pulaski's result is a baseline that's only achieved in structurally boring cases. If the coefficients B are richer, the bound has to get better.
And that leads to their claim. In this note, we prove a result of this form that is optimal up to a factor of n to the O1.
Let's quickly define that no term.
It's just a way of saying a subpolynomial factor. It's a term that grows slower than any positive power of n, like log n or log n2. When they say optimal up to this factor, they mean they've found the correct polynomial exponent, but their proof method introduces these small, annoying logarithmic terms.
Okay, so we've now established the central hypothesis. Diversity in the coefficients B must lead to stronger anti-concentration, beating Pulaski's baseline. Have we missed anything here?
No, I think that's perfect. We've identified the crucial constraint from Pulaski's work that n2 coefficients have to be identical for the worst case. And that's what creates the opening for this paper's contribution. Let's see how they formalize this in the language of probability.
All right, the next paragraph makes the language shift explicit. For the remainder of this note, we will use the language of anti-concentration, where for a random variable x, we let qx sup x be x is x.
So qx is the concentration function. It's just the probability of the single most likely outcome. A high qx means the variable is highly concentrated on one value.
And a low qx means it's highly anti-concentrated or spread out. Our goal is to find small upper bounds for qx.
Correct. And then they state Pulaski's theorem again, but in this language, this is theorem 1.1.
That A1, n be a set of n, 3 real numbers, and let B1, A, B, n be real coefficients, not all the same. If pi is a uniformly random permutation of n, then q of the sum is less than or equal to 1 to CL n2 plus 1.
So the random variable x here is the sum itself. The expression type is the random variable in the concentration function.
The latex is summi 1 AB pi.
The phonetic is the sum from I equals 1 to n of ai times b of pi of I. This just restates the geometric result in the probabilistic framework. Qx is bounded by roughly n1.
And the condition, not all the same for the bi's, is important.
Of course, if all the bi's were the same, say they were all just 1, then the sum would be sum a, which is a constant.
Yeah.
The probability of hitting that value is 1, so qx would be 1. That's the trivial case we want to exclude.
Okay, that completes the transition to the language of anti-concentration and formally presents the baseline. Theorem 1.1 by Pawlowski. Have we missed any nuances regarding the constraints on the coefficients?
I think we should emphasize one thing. The paper says A is a set, which implies its elements are distinct. But B are just coefficients, which can be repeated. They form a multi-set. This distinction is critical because, as we'll see, the paper's main result is all about the structure of the repetitions in B.
Got it. Let's proceed to their definition of that diversity statistic. ##3, defining diversity in Theorem 1.2, the main result. All right, now we get to the core technical innovation of the paper. Page 2, paragraph 1. To state our result for a multiset B, and you'll see B1 OE, we define its multiplicity profile, mu B, mu1, mu-L, to be the partition of N such that the distinct elements in B occur with multiplicities mu1 with mu, so L is the number of distinct elements in B.
Okay, let's do a deep digression on this. The multiplicity profile, mu B, is the key. It's a fingerprint that tells you exactly how redundant the multiset B is.
So mu1 is the count of the most frequent number in B, mu2 is the count of the second most frequent, and so on.
Exactly. Let's take two extremes. If B was a set of distinct elements, then every element appears once. So mu would be 1, 1, 1, 1, a list of n ones, and L, the number of distinct elements, would be n.
And the other extreme, if B were all the same number.
Then there's only one distinct element, so L is 1. That element appears n times, so mu1 is n. The profile mu would just be n.
Okay, so this profile captures the structure of the repetitions. Now, how do they turn this profile into a single number?
That's the next sentence. We additionally define MB semifinale I1 to me.
The expression type is the diversity statistic MB.
The latex is MI1.
The phonetic is capital M of B is the sum from I equals 1 to L of the quantity I minus 1 squared times mu E.
Let's really analyze this formula. It's simple, but it's very cleverly designed.
What's the first thing you notice?
The I12 factor. When I1, this factor is 1, 1, 2, which is 0.
Ah, so the most frequent element, the one with multiplicity mu1, contributes absolutely nothing to MB.
Exactly. The statistic is designed to completely ignore the most common element. It's a measure of how much diversity exists outside of that most dominant value. It's a measure of spread in identity.
And the I12 part puts a heavier and heavier weight on the less frequent elements. The second most frequent element, I2, gets a weight of 1. The third, I3, gets a weight of 4. The fourth gets a weight of 9.
Right. It heavily rewards having many distinct elements, which means having a large L. Let's check our extremes again. What happens in the worst case, low diversity, where all elements are the same?
Well, L is 1, so the sum only has one term for I1. The factor is 1, 1, 2 equals 0, so MB is 0.
It's actually slightly more subtle. If all elements are the same, the theorem doesn't apply. But if, say, N1 elements are the same and 1 is different, then L2, mu1, N1, U2, 1. The first term is 0. The second term is 2, 1, 2, 1, which is just 1. So MB is 1, very small.
And the best case, high diversity, where B is a set of distinct elements.
Then L is n, and all the mu e are 1. So MB is the sum of I12 as I go from 1 to n. That's O2 plus 12 plus 22 plus N12.
Which is a famous sum. It's approximately N33.
Exactly. So MB is a statistic that ranges from something very small, like 1 for highly repetitive sets, all the way up to something on the order of N3 for highly diverse sets.
Okay, that covers the definition of the multiplicity profile and the crucial diversity statistic, MB. We see why it's 0 or close to it if coefficients are nearly the same and large if they're distinct. Have we missed any foundational concepts here?
No, I think we have defined the engine that's going to drive their improvement over Pawlowski. We should just note that the condition for their theorem to apply will be MB0, which is just a formal way of excluding the trivial case where all coefficients are identical. Let's see the theorem itself.
Okay, here it is, Theorem 1.2. Let A1 and B at B1 be a set and a multiset, respectively, of real numbers such that MB0, if pi is a uniformly random permutation of n, then Q of the sum is less than or equal to, and here's the bound.
The expression type is the final concentration bound.
The latex is frac1 N101.
The phonetic is 1 divided by the quantity n to the power of 1 minus little o of 1 times the square root of m of b.
Let's analyze this bound. It perfectly captures the story. If MB is small, say MB is on the order of 1.
Then the denominator is just N101, so the bound is roughly N1, which is exactly Pawlowski's bound. It recovers the baseline perfectly.
And if MB is maximal, high diversity, so MB, is on the order of N3.
Then the denominator is N101 times the square root of N3, which is N3 too.
So you have N1, N1.5 in the denominator, which is N2.5.
And that gives you a bound of N2.5 or N52 with that little O1 loss. It confirms the result they advertised in the abstract. This one formula smoothly bridges the gap between the low diversity and high diversity regimes.
And let's re-emphasize that condition. A has to be a set here, meaning its elements are distinct.
Yes, they've essentially maximized the diversity of A to isolate the effect of B's structure. If A also had a lot of repeated elements, say A was mostly zeros, then the sum would be concentrated no matter what B looked like. By making A set, they ensure that the concentration is controlled solely by the structure of B, which is measured by MB.
This theorem perfectly quantifies the relationship between the diversity MB and the spread of the sum. Have we missed any nuances regarding the constraints?
I think we've covered it well. We must explicitly state that A is a set distinct elements, while B is a multiset with potential repetitions. This distinction is what puts all the focus on the MB statistic. Let's move on to the classical context for this result.
Okay, the next paragraph puts this result into historical context. Theorem 1.2 can be interpreted as a permutation analog of anti-concentration results of Erdős-Moser, Sarkozy-Semerady, Stanley, and Halász.
Right, so they're situating their work in a long and very famous line of research.
They start by recalling the classical problem. For context, we recall the classical problem of Littlewood and Offord, which asked for an upper bound on QX where X semi 1A12 with independent 12 and 0, 1.
This is the canonical problem of random sum, so let's do a deep digression. The 12 pronounced CI are independent Bernoulli random variables. You can think of them as coin flips.
So the sum X is a random subset sum of the coefficients A. You're basically flipping a coin for each A to decide whether or not to include it in the sum.
And the key word there is independent. The choice for A1 has no bearing on the choice for A2. This is fundamentally different from our permutation model.
How so?
In our model, the terms are A, B, P, I. They are highly dependent because the single choice of the permutation pi affects all the terms simultaneously. It's a much more rigid structure.
Okay, so back to the independent Littlewood-Offord problem. What was the baseline result there?
In 1945, Erdős proved the sharp universal bound QX is bounded by N12.
N to the minus 1/2. That's a much slower decay than the N1 we saw from Pawlowski in our problem.
Yes, but it's a different problem. The point isn't to compare the exponents directly, but to see how they change when you add structure.
Right, and that's the next sentence. It was later proven by Erdős and Moser that if the A are pairwise distinct, this bound can be improved to QX is bounded by N32 plus O1.
And there's the core analogy. In the independent model, making the coefficients distinct improves the concentration exponent from -12 to -32. It gets better by a full power of n.
So this paper is claiming to do the same thing for the permutation model. Taking the coefficients B from highly repetitive to fully distinct improves the exponent from -1 to -52.
Exactly. It's the same philosophical leap, just in a different setting. The next couple of sentences just add more historical detail, noting that Sarkozy, Semerady, and Stanley later removed the O1 term and got the optimal N32 bound.
And then they bring it back to Halász. Halász later strengthened this theory by showing that QX is controlled by the number of short-signed additive relations among the coefficients.
Which is what we discussed at the start. Halász showed that if the I have no hidden additive structure, the concentration is minimal. This paper is seeking the permutation analog, that same connection between structure and concentration.
Okay, we have placed theorem 1.2 squarely within the history of anticoncentration. It's an analog to the Erdős-Moser result, but for the harder permutation model. Have we missed any nuances in the comparison between the independent and permuted sums?
I think the distinction between the independent 12 variables and the dependent B by I coefficients is the most essential thing for you, the listener, to grasp. That dependence is what makes this problem so much more challenging. Let's see how they reiterate their mechanism.
The next paragraph brings it all together. Theorem 1.2 achieves an analogous result in the permutation model. Instead of considering additive energies, we quantify the relevant structure of the coefficient multiset B via its multiplicity profile, or in the statistic, MB.
So they're being explicit. MB is their tool for measuring structure, playing the role that additive energies, or short relations, played in the classical Halász theory.
Then they state their thesis very clearly. Our bound from theorem 1.2 can be read as stating that the more diverse B is, as measured by MB, the smaller the point masses of the permutation sum must be.
It's a direct quantifiable relationship.
And they revisit the two key examples. In particular, in the fully distinct regime one has, MB is approximately N3.
The expression type is asymptotic equivalence.
The latex is MB, approx N3.
The phonetic is capital M of B is approximately equivalent to N cubed.
Yielding a bound of N52 plus O1, which is exactly what we calculated before.
And then the other side of the coin. On the other hand, in the highly repetitive regimes, the estimate is consistent with the universal n to the minus 1 type bound of Pawlowski.
So it shows how their MB statistic provides a smooth transition between their new, stronger result and the existing baseline. It unifies the theory.
Precisely. And there's a footnote here, which is interesting.
Footnote 1. While we were preparing this manuscript, this corollary was also independently obtained by Dongguyen Fan-Tran Vu, as well as several other interesting results about this permutation model.
This is very common in active research fields. It just shows that this was an important, timely problem, and multiple groups were closing in on the answer at the same time. It's good academic practice to acknowledge that.
Okay, that concludes the discussion of the primary result, Theorem 1.2, and its historical context. We see how MB seamlessly integrates the low diversity and high diversity results. Have we missed any nuances here?
I think we should just reiterate that MB is the key technical contribution. It's the structural parameter that replaces Halász's number of short additive relations for this new model. Let's look at their generalization next.
All right, so far we've assumed that the set A is made of distinct numbers. The next theorem relaxes that. We also prove a result where A is allowed to have repeated elements.
This is theorem 1.3. Let A and B be multisets of real numbers, such that MAB is greater than or equal to N3 plus epsilon for some epsilon 0. If pi is a uniformly random permutation, then Q of the sum is bounded.
Okay, let's break this down. First, the condition. The expression type is the condition for theorem 1.3 involving the product of diversity statistics.
The latex is MAMB, get share N3 plus epsilon.
The phonetic is capital M of A times capital M of B is greater than or equal to N to the power of 3 plus epsilon.
And now the bound itself. The expression type is the bound in theorem 1.3.
The latex is Q sum I1 VRAC N2.
The phonetic is Q of the sum is bounded by epsilon, by N to the power of 1/2 times the quantity logarithm of N squared, divided by the square root of capital M of A times capital M of B.
So the crucial difference here is that anti-concentration now depends on the product of their diversity measures, MA, MB.
Right. It's the combined structural richness of both multi-sets that matters. But what's really interesting is that strict threshold condition, MAMB, must be bigger than N to the 3 plus epsilon. Why is that there? Why doesn't the theorem just apply all the time?
It seems like it needs a certain critical mass of diversity to get started.
That's a good way to put it. The proof technique relies on having enough collective diversity between A and B to work. If one of them is too structured, like in the counterexample we'll see, the whole thing can fall apart and you can get high concentration.
And the paper notes this is unusual. We note that theorem 1.3 has the unusual statement that the bound is either relatively strong or non-existent.
Right, it's a gonna-go theorem. If you meet the threshold, you get a strong bound. If you don't, the theorem tells you nothing.
Okay, that establishes the generalized result, theorem 1.3. It's controlled by the product MAB, but it requires this high diversity threshold. Have we missed any nuances in the formula?
I think we should just keep an eye on that log N2 factor in the numerator. That's another source of the no loss we've been talking about. It's a clue about where the imperfections in the proof technique lie. Let's get to the tightness discussion.
The next paragraph is all about showing these results are sharp. Let us also remark that theorem 1.2 and theorem 1.3 are tied up to subpolynomial factors.
So they're claiming they've got the polynomial part right. To prove this, they construct a case and calculate the variance.
The setup is a bit technical, but they essentially construct multisets A and B with specific controlled repetition patterns. And then they compute the variance of the permuted sum.
And the result is really clean. The expression type is the variance of the permuted sum.
The latex is text far eprakos.
The phonetic is the variance of the sum is approximately equivalent to capital M of A times capital M of B divided by N.
So let's do a quick digression on variance and concentration. How does one lead to the other?
Well, variance, sigma 2, is the most basic measure of how spread out a distribution is. A high variance means the data is far from the mean. on average.
Right. And there are inequalities like Chebyshev's inequality that connect variance to probability.
Exactly. Chebyshev's inequality gives a very rough bound on concentration. But here, since their constructed sets A and B are all integers, the sum is also an integer. So they can use a slightly stronger argument with the pigeonhole principle.
And what does that give them?
It gives them a lower bound on the concentration. It follows that Q of the sum is bounded below by N12 square TMB.
Let's see that again. The expression type is the lower bound on concentration.
The latex is Q sum IBE BAA. The phonetic is Q of the sum is bounded below by N to the power of 1/2, divided by the square root of capital M of A times capital M of B.
Now compare that to the upper bound from theorem 1.3.
The upper bound was N12 log N2 over the same denominator. They match perfectly, except for that log N2 factor. This proves their result is tied up to that subpolynomial logarithmic loss. They've nailed the main term.
Okay, so the result is sharp. Now they have to prove that the threshold condition was necessary. Moreover, the condition of MA/MB equal N3 plus epsilon in theorem 1.3 is necessary.
And they do this with a brilliant, simple counterexample. The setup is if A floor N2 union 0, 0, 0, 0 and B 1, 0, 0, 0.
Let's trace this. A is half zeros, and the other half are the distinct integers from 1 up to about N2.
Right, so B is almost all zeros except for a single 1.
Now let's calculate the M statistics. B has minimal diversity. Me1 is N1 for the 0. Me2 is 1 for the 1. We calculated this before, and Me is just 1.
Right, and A, the most frequent element, is 0, with multiplicity of about N2. The other N2 elements are distinct, so when you calculate MA, you're summing the squares of ranks for those N2 distinct elements. This gives you something on the order of N3.
Okay, so in this example, MA is roughly M3, and MB is 1. What's the product?
The product MAB is approximately N3.
Which violates the N3 plus epsilon condition required by the theorem. So theorem 1.3 should not apply here.
Exactly. It's right on the edge, but it fails the test. Now let's look at the actual concentration. On the other hand, sum A BPI is simply the single value of A matched to the unique non-zero entry of B.
Since B is all zeros except for a single 1, the sum is just whichever A gets paired with that 1.
It's just a uniformly random element of A.
And since A contains at least N2 zeros,
we have Q of the sum is greater than or equal to the probability that the sum is 0, which is greater than or equal to 12.
That is massive concentration. The probability of getting 0 is at least 50%.
Which is a constant. It's not decaying at all, let alone polynomially. This is a highly concentrated example, and it proves that if your diversity product is only on the order of N3, the theorem can fail spectacularly. The N3 plus epsilon threshold is absolutely necessary.
This section beautifully demonstrates the sharpness of the results. It gives a lower bound showing near tightness, and this critical counterexample proving the necessity of the diversity threshold. Have we missed any nuances in the counterexample structure?
No, I think the structure is perfect. The unbalanced diversity one set is highly diverse in its non-zero part. The other is minimally diverse. Is the perfect illustration of how you can fail the required threshold. Let's look at the setup for the proofs now.
The next paragraph gives a brief overview of the proof. We discuss the proofs of Theorem 1.2 and Theorem 1.3 in Section 2.
And then it names the key ingredient. An important ingredient is a Minkowski distance energy result of Roche-Newton and Rudnev, which in turn relies on a deep incidence theorem for points and lines in R3 due to Guth and Katz.
Okay, let's do a deep digression here. This is a profound connection. Why does a problem about anti-concentration of sums rely on incidence geometry, how points intersect lines or planes in 3D?
It's one of the deepest themes in modern combinatorics. The additive structure of a set of numbers can be translated into the geometric structure of a set of points.
Right.
Sets with a lot of additive structure, like arithmetic progressions, correspond to points that are highly structured, like lying on a line.
I see.
The Guth-Katz theorem is a landmark result that basically says that a large set of points in 3D space cannot have too many lines that each contain many of the points, unless the points themselves have a very specific, rigid structure, like lying on a plane. It provides a powerful constraint on how random geometric configurations can be.
And Roche-Newton and Rudnev managed to translate that geometric rigidity into a statement about the additive energy of sets of real numbers.
Correct. They showed that sets of real numbers can't have too much additive structure, because if they did, it would violate these deep geometric constraints. This paper is leveraging that deep structural result to control the concentration. The Guth-Katz result, by the way, was originally developed to solve the famous Erdő's distinct distances problem. It's an extremely deep piece of mathematics being repurposed here.
So that sets the stage for the proofs, highlighting this reliance on advanced techniques from incidence geometry. Have we missed any nuances about the source of the technical strength here?
I think we've established it. The depth of this result comes not just from probability, but from importing these recent powerful theorems from a completely different area of math algebraic geometry and combinatorics. Let's move on to the notation block. Hashtag tag changes 4Ts. Notation and preliminaries.
All right, the next few paragraphs are just setting up notation. First, N denotes the set 1, N, standard stuff.
Then they define the asymptotic notation. F is bounded by G. F less mg means F CG for some constancy.
Okay, the expression type is bounded by.
The latex is F less mg.
The phonetic is F is bounded by G.
And then F is approximately equivalent to G. F approx G just means it's bounded above and below by G.
Got it. The expression type is approximate equivalence.
The latex is F approx G.
The phonetic is F is approximately equivalent to G.
The next paragraph introduces a slightly more complex idea, conditional concentration. Given two random variables, x and y, we let qxy denote the random variable fy, where fy equals sup x, px, xy equal y.
Okay, so this is the concentration function of x, but after we already know the value of y.
Right, and it's important to realize that since y is a random variable, qxy is also a random variable. It's a function of y.
Its value depends on the outcome of y.
Yes, and the reason they define this is for the next fact, which is a crucial technical tool. We will often use the fact that qx is less than or equal to ey qxy.
So the overall concentration is bounded by the average of the conditional concentrations.
This is a huge simplification. It's a divide and conquer strategy.
Yeah.
If you can show that, on average, the concentration is low after conditioning on some other variable, then the total concentration must also be low. We'll see them use this in the main proof.
That defines all specialized notation, including that crucial property of conditional concentration. Have we missed any nuances?
I think it's just vital to emphasize that qxy being a random variable itself might be a bit confusing. You just have to remember it's a function, fy, whose value for any outcome y of y is the max probability for x given that outcome. Let's proceed to the acknowledgments.
Okay, the last paragraph on this page is the acknowledgments. We thank Noga Alan for helpful conversations.
A giant in the field. Not surprising he'd be involved in discussions on a topic like this.
Then they list funding sources. CP was supported by an NSF grant, and DZ was supported by the NSF Graduate Research Fellowship Program.
Standard, but important for recognizing how research is funded.
Okay, that completes the first section of the paper, the context, the theorems, the constraints, and the acknowledgments. Have we missed any final details before we dive into the proofs?
We have completed all the introductory material. I think we're ready to get into the technical core of the paper, starting with the proofs in Section 2.
All right, Section 2 begins. We begin with a few probabilistic preliminaries. We first state a standard Chernoff bound. This is fact 2.1.
Let n be a positive integer and 0 delta p1 be real numbers. If x is the sum of n independent key Bernoulli variables, then the probability that x is less than or equal to 1 delta pn is less than or equal to e to the delta 2 pn2.
So a deep digression here. The Chernoff bound. Why is this necessary? What is it for?
The Chernoff bound is one of the most powerful tools in probability. It's a concentration inequality. It tells you that if you have a sum of many independent, random, coin flip-like variables, that sum is extremely unlikely to be far from its expected value.
The expected value here is Pm.
Right, and the bound tells you the probability of deviating from that expectation decays exponentially fast. It's a guarantee that randomization works reliably. If you expect to get 50 heads out of 100 coin flips, Chernoff tells you the probability of getting only 10 heads is astronomically small.
I see. So they'll need this to show that some random sampling process in their proof behaves as expected.
Exactly. Let's just state the formula formally. The expression type is the Chernoff bound inequality.
The latex is Px, Pst, E delta Pn2.
The phonetic is the probability that x is less than or equal to the quantity 1 minus delta times p times n is less than or equal to e to the power of minus delta squared times p times n divided by 2.
Okay, that covers the standard Chernoff bound, fact 2.1. Have we missed any nuances regarding its role as a guarantee of probabilistic expectation?
No, I think we've established that this is a tool for controlling concentration in the independent setting. The next step will be to adapt it to the dependent setting of their problem. Let's see, proposition 2.2.
Okay, via a conditioning argument, this leads to the following corollaries. And here's proposition 2.2. The setup is a bit different. If S is a uniformly random Pn element subset of n.
Stop right there. This is crucial. S is a subset of a fixed size. We're not flipping a coin for each element anymore. We are choosing exactly Pn elements out of n.
And that introduces dependence. If element 1 is chosen, it slightly reduces the chance for element 2 to be chosen. This is a hypergeometric distribution.
Exactly. It's not the independent Bernoulli variables from the Chernoff bound. But the conclusion looks very similar. It bounds the probability that the size of the intersection of S with some smaller set M is small. It's saying that even this dependent sampling process still behaves, for the most part, like the independent one.
So how do they prove that?
The proof is a really elegant conditioning trick. They say, let's invent a different random set, S, where we do sample every element independently with probability P.
So S is a binomial random variable. Its size is not fixed.
Correct. Now, the key insight is that our fixed size set S has the same distribution as S conditioned on the event that the size of S happens to be exactly Pn.
I see. So they can relate the dependent process to the independent one.
Yes. And it's a well-known fact that the probability of S having exactly size Pn, which is its peak probability, is at least 1n plus 1.
The expression type is the probability lower bound for the size of S.
The latex is PSS is PS, Pn, GAC, frame 1 plus 1.
The phonetic is the probability that the magnitude of S prime is equal to P times n is greater than or equal to 1 over n plus 1.
So using Bayes' rule, they can relate the probability for S to the probability for S, but they have to pay a price. That price is a factor of n plus 1.
And now the probability they need to bound is about S, which is the sum of independent variables.
So they can just apply the Chernoff bound from fact 2.1 directly. The proof is done. The final bound has an extra n plus 1 factor, but it still has that crucial exponential decay.
Okay, that covers proposition 2.2. It's a clever way to leverage the Chernoff bound for fixed-size subsets using a conditioning trick. Have we missed any nuances in that proof structure?
I think we've identified the key part. The 1n plus 1 factor is the price you pay for turning a dependent process into an independent one for the sake of the proof. Let's proceed to proposition 2.3, which adds another layer of complexity.
All right, proposition 2.3, the setup. Let m n be positive integers such that 2 equals n. Let S and T be uniformly random Pn and Q element subsets of n, respectively, chosen independently from each other.
So now we have two independent fixed-size subsets. S has size Pn, T has size Qn.
Then they define a special set of indices I, if I is the set of indices I in M, such that 2i1, 2i intersect S1 and 2i1, 2i intersect T1.
Let's stop and unpack that definition. They're looking at pairs of indices like 1, 2, 3, 4, etc., up to 2 mem 1, 2 meter.
And the condition 2i1, 2i intersect S is 1 means that for the pair 2i1, 2i, exactly one of them is in the set S and one is not.
We can say the pair is split by S.
So the set I counts the number of pairs that are split by both S and T simultaneously. This feels like a very specific mechanism. It must be central to the main proof later.
It absolutely is.
Yeah.
This is the mechanism that will generate the independent variables for the Halász trick. The proposition then gives a Chernoff style bound on the size of this set I.
And the proof.
It's the exact same conditioning trick as before, just applied twice. They introduce independent sets S and T, which turns the problem into one about independent Bernoulli variables. But since they condition on the sizes of both S and T, they pay a price of n plus 1, 2 this time.
And the goal is to apply the Chernoff bound to the size of the independent version I. To do that, they need the probability that any single pair is in I.
Right, and they calculate it. For a single pair in the set S, with sampling probability P, what's the probability it gets split?
Well, there are two ways. Either the first element is in and the second is out, probability P, 1P, or the first is out and the second is in, probability 1PP. So the total is 2P, 1P.
Perfect. And for the set T, it's 2Q, 1Q. Since S and T are independent, the probabilities of a pair being split by both is the product.
4P, 1P, Q, 1Q.
Exactly. And since the events for each pair I are independent, the size of I is just a sum of m independent Bernoulli variables. So the Chernoff bound applies directly, and the proof is complete.
That completes the probabilistic preliminaries. Proposition 2.3 gives them control over the expected number of these split pairs in two random subsets. Have we missed any nuances in that probability calculation?
No, I think that's clear. We've established that 4P1P Q1Q meter is the expected number of these split pairs, and the proposition guarantees that with very high probability, the actual number will be close to this expectation. This will be vital for a coloring argument they use later. Let's move to how they define additive structure.
The next part of the paper introduces a new technical concept, We now introduce a notion of additive structure, which will be useful for the proof. This is definition 2.4.
The setup is, let A and B be non-empty multisets of real numbers, and C, C1, CS, is a tuple of non-zero integers.
Then they define a quantity KCAB. It's the number of forced tuples of indices such that, and then there's a big sum.
Let's look at that sum. It's the core of the definition. The expression type is the zero-sum condition for KC.
The latex is sum K1 AB Bano. The phonetic is the sum from K equals 1 to S of CK times the quantity of sub IK minus a sub JK times the quantity of B sub IK prime minus B sub JK prime equals 0.
Okay, deep digression on additive energy. What is this KC counting? What does it mean? KT is a generalized form of what's called additive energy. It's a measure of how much algebraic structure exists between the sets A and B. It's counting how often a specific weighted sum of products of differences equals 0. The A terms are differences within set A. The B terms are differences within set B.
Right. And KT counts the number of ways that S of these products of differences, when weighted by the coefficients AC, happen to cancel out perfectly and sum to 0.
So a large value of KT means there's a lot of this kind of structure.
A huge amount. And from Halász's work, we know that additive structure is the enemy of anti-concentration. A large KT is bad. It means the sets are structured in a way that will likely lead to high concentration.
Then they define a variant, KCAB. It's the same count, but with the additional condition that all the I and J indices are distinct from each other, and all the I and J indices are also distinct.
This is the restricted version. It's a technical convenience. It simplifies the analysis later by getting rid of trivial solutions like if HEK, that term is just 0 automatically. And finally, they normalize these counts. They define CAPAC and CAPEC by dividing by the total number of possible tuples.
Right, so the kappa values are densities. You can think of CAPAC as the probability that a randomly chosen collection of differences satisfies the zero-sum condition.
Okay, that defines these complex measures of additive structure, kappa C and CAPAC. They count the ways two sets can interact algebraically to produce a zero sum, which indicates high structure and potentially high concentration. Have we missed any nuances in the indices?
I think we've emphasized the meaning of the index constraints for the restricted version CAPC and the normalization factor. That's just a total number of ways you could choose the indices if there were no restrictions. Let's look at lemma 2.5, which connects this structure to anti-concentration.
All right, this looks like a major step. Lemma 2.5, the setup. Let A and B be multisets of real numbers, neither of which contain more than 2 any 3 copies of a single element.
Okay, stop there. That 2 and 3 condition is really important. It's a technical assumption that basically says that A and B must have at least some minimal amount of diversity. They can't be overwhelmingly dominated by just one value.
So we're ruling out the most trivial, highly concentrated cases from the start.
Right. And now for the conclusion. Then for any D0, there exists a finite set C of tuples, such that Q of the sum is bounded by ND plus sum C in C kappa C A B N12.
Let's look at that bound. The expression type is the main bound in lemma 2.5.
The latex is Q sum ND plus sum D A B ND. The phonetic is Q of the sum is bounded by D, by n to the power of minus D, plus the sum over C in C of kappa prime C of A and B times n to the power of 1/2.
Let's analyze this. What's the so what here?
The bound has 2 parts. The first part is ND. Since we can choose D to be any positive number, we can make this term arbitrarily small. N100, N1000. It's a negligible error term.
Exactly. So the real story is the second term. The concentration is dominated by the sum of kappa sec, the density of zero-sum relations. This is the bridge. It formally states that if the additive structure CAPIC is low, then the concentration Q is low. And if the additive structure is high, the concentration is high. It connects the two directly.
This is the heart of their Halász type argument.
Okay, that establishes lemma 2.5. It provides a handle on the concentration function by relating it to this normalized density of additive relations CAPIC. Have we missed any nuances in that required diversity condition?
The 2 and 3 threshold is what enables a complex randomization trick they're about to use. It guarantees that the sets aren't so lopsided that the trick fails. Let's dive into the proof of this lemma, which starts with Halász's theorem itself.
Right. The proof begins. To prove lemma 2.5, we will use the aforementioned anti-concentration bound of Halász. This is theorem 2.6.
And this is the classical theorem for the independent model. The setup is A1, Rmon, and R non-zero reals, and Vi1, Salasin are independent random variables, uniform in 0, 1.
The coin flips again.
Then Q of the sum is bounded by RR into R12.
Okay, so the concentration depends on this quantity RRQ. What is that?
The expression type is The number of zero-sum relations are.
The law text is R.
The phonetic is capital R sub R. And RR is defined as the number of choices of two R indices and two R signs, plus or minus 1, such that the corresponding sign sum of the i's equals 0.
So a deep digression on Halász's mechanism, RR is literally counting the number of additive relations of length 2R within the set A.
Exactly. A large RR means the set A has a lot of this hidden additive structure. And Halász's theorem shows that this structure is what controls concentration. The brilliant part is that R can be any positive integer. If you have very, very little structure, R will be small, even for large R, and you can get an incredibly strong bound on Q faster than any polynomial.
Okay, that covers the introduction of Halász's theorem. It shows concentration is governed by the number of additive relations for the independent model. Have we missed any nuances here?
We just have to keep emphasizing, this theorem is for independent variables 12. Our problem is about the dependent permutation variables. The whole magic of the proof is how they bridge this gap.
And the next paragraph reveals that magic. To apply this theorem, let m equals florin 2, let pi be a uniformly random permutation independent from pi, and let sigma be a random permutation obtained by taking the product of a uniformly random subset of the m transpositions 1, 2, 3, 4, weak, 2 middle to 1, 2 midders.
Okay, this is a very complex randomization strategy. Let's break it down. They introduce a whole new random permutation pi.
And then this other thing, sigma. What is sigma?
Sigma is built from simple swaps. You have m pairs of indices, 1, 2, 3, 4, and so on. For each pair, you flip a coin. If it's heads, you include the swap in sigma. If it's tails, you don't. So sigma is a random collection of these pair swaps.
And this is what's going to introduce the independence they need for Halász's theorem.
Exactly. The next sentence shows how. They claim that the sum api gap has the same distribution as our original sum.
So they can study this more complicated object instead, and then they use that conditional concentration trick we saw earlier. Q of the sum is bounded by the expected value of Q of this new sum, conditioned on pi and pi.
This is the key step. They freeze pi and pi. The only randomness left is from sigma, which is just that collection of independent coin flips.
And now they rewrite the sum. Letting squ be the indicator variable of the occurrence of the swap, 2i1, 2i in sigma, we have a new expression for the sum.
And that expression is a fixed constant term minus a random sum that looks like sum I1 to 12 sig.
And the 12 are our independent Bernoulli variables. It's exactly the setup for Halász's theorem.
It's an absolutely ingenious trick. They've transformed the dependent permutation sum into a form where Halász's theorem applies. The new coefficients, the C, are these products of differences, AP2I1, AP2I, BP2I, and PR2I.
This covers the randomization trick. It's a way to turn the dependent sum into a fixed term minus a sum involving independent variables, making it suitable for Halász's theorem. Have we missed any nuances in the coefficient structure?
Yes. An important detail is that these new coefficients C can be 0. For instance, if AP2I1 happens to equal AP2I, the application of Halász's theorem has to ignore these 0 coefficients, so they need to make sure there are enough non-zero ones.
Right, and that's what they tackle next. They define a pair of permutations, P, as good if there are at least M10 non-zero coefficients C.
This goodness condition just ensures that the random part of the sum is actually random enough for the theorem to be meaningful.
So for a good pair, they can apply Halász's theorem and they get a bound on the conditional concentration. That bound depends on RO pi, which is the number of additive relations among these new coefficients C.
And this leads to the overall bound. We conclude that Q of the sum is bounded by 2 terms. The probability that P is not good, plus the expected value of the Halász bound in the good case.
So they have to bound 2 things. First, the probability that their randomization trick fails.
Right. And to do this, they use a clever coloring argument. They claim they can color the elements of A and B with red and blue such that the number of red elements in both multisets is balanced between N3 and 2 and 3.
Why is that possible?
It's possible because of that 2 and 3 assumption from the start of the lemma. It guarantees the sets aren't so lopsided that you can't find a balanced partition.
And how does this coloring help?
With this coloring, they could apply proposition 2.3, that probabilistic preliminary about split pairs. They can show that with overwhelmingly high probability, there will be at least M10 pairs where both the A's and the B's get different colors.
And if the colors are different, the elements must be different, so the difference is non-zero.
Which means the coefficient C is non-zero. So this guarantees that the pair, pi is good.
And the probability of failure.
It's bounded by something that decays exponentially fast. like n plus 1, 2 e alpha. This becomes the ND error term in the lemma's statement. It's completely negligible.
Okay, that concludes the error term analysis. The probability of the randomization trick failing is exponentially small. Have we missed any nuances regarding that exponential decay?
No, the exponential decay is the whole point. It guarantees that for any reasonably large n, this failure case is totally insignificant compared to the other term, the one controlled by the additive structure. Let's analyze that term now.
Right, so now we need to bound the expected number of zero-sum relations, ERR pi.
They look at the condition for a zero-sum relation among the CJ coefficients. They note that there are some trivial cases, about ONR of them, which is a small number of the total n2 possibilities. These are negligible.
And for all the other non-trivial choices.
This is the core algebraic step. They show that for these choices, the probability that the zero-sum relation holds is, on average, exactly kappa CA.
The very same measure of additive structure they defined back in definition 2.4.
This is the payoff. The number of relations in their randomized setup, RR pi pi, is directly controlled by the intrinsic additive energy kappas of the original sets A and B.
So the expectation ERR, pi, is bounded by some negligible polynomial term plus n2 times the sum of these kappa terms.
And when you put everything together, the exponential error from the not good case, the negligible error from the trivial relations, and this main structural term, you get the final bound from the lemma.
Which was Q of the sum is bounded by ND plus some cubic N12.
Right. They can choose R to be large enough to make all the other error terms smaller than ND, and this finishes the proof of the lemma.
Wow. Okay, that completes the lengthy proof of lemma 2.5. They successfully translated the permutation anticoncentration problem into an analysis of this generalized additive energy kappa via the Halász method and the coloring trick. Have we missed any nuances in the final deduction?
No, I think we've seen the whole arc. The problem's complexity has now been reduced to just one task.
Right.
Find a good, uniform upper bound on the additive energy kappa B. And that's where the incidence geometry comes in.
The next step is lemma 2.7. The next lemma is a uniform estimate for every kappa AB with input from incidence geometry.
And here's the statement. Let A and B be finite sets of real numbers of size at least 2. Then for any C, kappa AB is bounded by log A plus log B, AB.
The expression type is the uniform estimate for the density of zero-sum relations.
The latex is kappa AB, let's some frac log A plus log B.
The phonetic is kappa C of A and B is bounded by the quantity logarithm of the magnitude of A plus logarithm of the magnitude of B divided by the magnitude of A times the magnitude of B.
This is a critical result. It says that no matter how complex your relation C is, the density of that additive structure is always small. It decays like 1 over the product of the sizes of the sets.
And that decay comes from the rigidity of geometry.
Precisely. The proof is interesting. They say that the result from Roche-Newton and Rudnev, which is the one that relies on Guthkats, only applies directly to the simplest case, kappa 1, 1.
That's where C1 like 1.
Right, so all they need to do is show that the general kappa is always less than or equal to this simple kappa 1, 1.
And how do they do that?
It's another elegant technical trick. They define a random variable z as the product of two random differences. They note that kappa is just the probability that a weighted sum of independent copies of z equals 0.
Then they use conditioning and the Cauchy-Schwarz inequality.
And that shows that this probability is always maximized when you're just asking for the probability that z1 equals z2, which is exactly kappa 1-1. The proof is complete.
So the general complexity is always bounded by the simplest complexity, and the simplest complexity is bounded by the deep result from incidence geometry.
A beautiful chain of reasoning.
That establishes lemma 2.7, showing the density of additive structure. Kappa is uniformly low due to these underlying geometric constraints. Have we missed any nuances about the source of that logarithmic loss?
Yes, this is the perfect place to point it out again. The log A plus log B factor in the bound comes directly from the limitations of the Roche-Newton and Rudnev result.
And that's because of things like grid examples in the underlying geometry problem.
Exactly. It's an artifact of certain highly structured point sets that prevent a cleaner bound. This logarithmic loss is the direct source of the Nath factor in the final theorems of the paper.
Okay, let's move to lemma 2.8, which looks like the final technical bridge. Lemma 2.8. The setup here seems to be about structured multisets. Suppose A contains as a submultiset M copies of a set A of size R, and B contains m copies of a set B of size R.
Right, so they are formalizing what it means for A and B to have structured repetitions. A and B are the core sets of distinct elements. R and R are their sizes, a measure of diversity, and M and M are their multiplicities, a measure of repetition.
And there's another threshold condition. MAM must be greater than or equal to N1 plus epsilon.
This just ensures there's enough total stuff in these structured parts to be meaningful. The product of the total number of elements in these structured subsets has to be a little bigger than n.
Okay, and if that condition holds, what's the conclusion?
Then Q of the sum is bounded. The expression type is the bound in lemma 2.8.
The latex is Q sum my log, less M1, less M log, My my MR. The phonetic is Q of the sum is bounded by epsilon, by n to the power of 1/2 times the logarithm of n, divided by the product of the square root of m times m prime and r times r prime to the power of 3/2.
Wow, okay. That denominator is packed with structure. It depends on the multiplicities m and the diversities r and r.
This is the crucial technical result that connects those structural parameters directly to the concentration bound.
That covers the statement of lemma 2.8. Have we missed any nuances in the parameters?
I think we should highlight that the exponents are different. The multiplicity term m is under a square root, so it's to the power of 12. But the diversity term r is to the power of 32.
So the diversity of the underlying sets has a much stronger effect on lowering concentration than just the number of times those sets are repeated.
Exactly. Diversity is more potent than repetition. Let's trace the proof steps.
The proof of lemma 2.8 seems to involve another careful sampling process. Yes. They break down the random permutation pie into several steps. First, they determine E, which is the number of pairings that happen between the structured part of A and the structured part of B.
Then they choose the specific indices I and I that get paired up. And finally, they choose the random bijection between those chosen subsets.
The core idea is that the concentration of the whole sum is going to be controlled by the concentration of the subproblem, the sum just over these paired structured parts.
First, they have to make sure that E, the size of this subproblem, is large enough.
And they use proposition 2.2 for that. Since ER is bigger than N1 plus epsilon, they can show that the probability of U being smaller than its expectation is exponentially small, so they can just assume U is large.
Then they have to make sure the subproblem itself has enough internal diversity.
Right. They need to satisfy the conditions of lemma 2.5. So they use proposition 2.2 again to show that, with very high probability, the subsets of elements corresponding to I and I don't have any single value that appears more than 2U3 times.
Okay, so that covers the setup. They've used their probabilistic tools to guarantee that the subproblem they're about to analyze is large enough and diverse enough. Have we missed any nuances in the connection to proposition 2.2?
Just that the repeated use of proposition 2.2 is the probabilistic foundation of this whole proof. It lets them control the size and the internal structure of the random subsets they're working with. Let's get to the final bounding steps.
Okay, so once they have this well-behaved subproblem, they can apply their main lemma. Under these assumptions, lemma 2.5 applies.
Right, and lemma 2.5 says the concentration of the subsum is controlled by the additive energy, the kappa check, of the corresponding submultisets.
So now they just need to bound the expected value of that kappa check.
And this is the final payoff. They show that the expected additive energy of the random subproblem is bounded by the intrinsic additive energy of the core sets A and B, which, by lemma 2.7, the geometry result is bounded by log n.
And there it is. The structural parameters R and R from the setup have now appeared in the bound on the additive energy.
Exactly. When they put all the pieces back together and average over everything, they get a final bound with a few error terms.
They say the final bound is negligible error terms plus unlog n divided by m.
It's slightly different from the final statement. There's a factor of n12 difference, but the logic is the same. The first terms are all exponentially or polynomially small error terms that can be ignored.
And the main structural bound dominates, giving them the relationship they wanted.
Yes. This concludes the proof of the main technical lemma.
That completes the lengthy proof of lemma 2.8. It's an amazing synthesis of the randomization from Halász, the geometric bounds on additive energy, and the probabilistic control from the Chernoff type arguments. Have we missed any nuances in the dependency on epsilon?
The dependence on epsilon is critical. It's hidden in that less m epsilon notation. It reminds us that the constants in the inequality get worse as epsilon, the parameter, and the diversity threshold gets smaller. It's a technical but important point. Now for the concluding proofs of the main theorems.
All right, the final page of proofs. Given lemma 2.8, theorems 1.2 and 1.3 follow from a short dyadic partitioning argument.
The first step is another proposition, proposition 2.9. This is the bridge that connects their abstract diversity statistic MA back to the concrete structural parameters M and R used in Lemma 2.8.
And what does it say?
It says that any multiset A with MA greater than 0 must contain a substructure of M copies of a set of size R, where R is at least 2, and the product MR3 is at least MA ln Ben.
So it's a guarantee. If your MA is large, you are guaranteed to find a substructure inside A that has either high multiplicity M or high diversity R, or both.
Exactly. The proof is a neat little contradiction argument using an integral approximation for the sum of 1i. It shows that if such a structure didn't exist, MA would have to be less than MA, which is impossible.
Okay, that establishes proposition 2.9. High MA implies high MR3. Have we missed any nuances?
Just that there's another log n loss here. This structure finding step isn't perfect, and it introduces one more source for the net factor in the final answer. Let's move to the proof of theorem 1.3.
Okay, the proof of theorem 1.3. How does it work?
It's a straightforward application now. They use proposition 2.9 on both A and B to find structured subsets inside them.
So they find parameters M, R, MR that are related to MA and MB.
Then they check the condition for lemma 2.8. They use the theorem's assumption that MAMB is greater than N3 plus epsilon. This is strong enough to imply that MAR is also greater than N1 plus epsilon for some other epsilon.
So the condition for their main technical lemma is satisfied.
Which means they can apply it. The conclusion of lemma 2.8 gives them the bound in terms of MA.
Yeah.
Then they just substitute the relationship from proposition 2.9 back in, and it simplifies to the final bound in terms of MA. And proof is complete.
That completes the proof of theorem 1.3, successfully derived from the main technical lemma and the structure finding proposition. Have we missed anything?
No, I think the key takeaway is seeing how the abstract MAMB parameter successfully controls the denominator of the bound, proving that combined structural richness drives down concentration. Let's do the final proof for the main result, theorem 1.2.
All right, the proof of theorem 1.2. This is the case where A is a set of distinct elements, and the bound is in terms of MB alone.
They handle this with a simple case analysis. Case 1. The combined diversity MAB is very high. Let's say it's greater than N3 plus epsilon.
In that case, theorem 1.3 applies directly.
Right. And since A is a set, they know MA is on the order of N3. When you plug MA, N3 into the bound from theorem 1.3, it simplifies to something that is much stronger than the bound they actually want to prove. So it holds in this case.
So what's case 2?
Case 2 is that the combined diversity MAB is low, less than N3 plus epsilon.
But wait, we know MA is large, around N3.
Right.
So for the product to be small, MB must be very, very small. It must be less than epsilon.
Exactly. So this is the low diversity regime for B. And in that case, they don't need their fancy new theorem. They can just use Pawlowski's original theorem, theorem 1.1.
Which gives a bound of N1.
And they just show, with a little algebra, that N1 is also less than or equal to the bound they're trying to prove because MB is so small. So the bound holds in this case too.
So since it holds in both the high diversity and low diversity cases, it must hold everywhere.
And since the epsilon they used to split the cases was arbitrary, it can be made arbitrarily small, which is what gives the final factor. The proof is done.
That finalizes the proof of theorem 1.2 by showing that the two cases, high diversity, where theorem 1.3 applies, and low diversity, where Pawlowski's theorem controls it, coalesce into their unified bound.
Have we missed any nuances?
No, I think we have completed the entire argument structure for both main theorems. Let's move into their concluding remarks and conjectures for the future. #tag 13, section 3. Concluding remarks. Okay, section 3, concluding remarks. They start by reviewing their main result for the distinct set case. The bound of N52 plus O1 is a permutation analog of the Erdős-Moser theorem.
But they point out that the classical story went one step further. It is therefore natural to ask whether one can take this analogy even one step further and remove the loss completely.
In the spirit of the Sarkozy, Samardi, and Stanley results for the original problem.
Right. And this leads to conjecture 3.1. They conjecture that for sets A and B of distinct numbers, the concentration is bounded by a sharp constant times N52.
And what's the constant? The expression type is the conjectured sharp constant.
The latex is frac1 plus O1 N52.
The phonetic is the quantity 1 divided by 2 times the square root of 2 times pi plus little o of 1 times n to the power of minus 5/2.
This is the ultimate goal for this problem, a perfectly sharp exponent and a precise leading constant.
Where does that constant come from?
They believe the extremal case, the one with the highest concentration, should be when A equals B equals N, just the integers from 1 to N. In that case, the distribution of the sum should look like a Gaussian, a normal distribution. That constant is derived from the peak of that corresponding Gaussian.
But they say proving this would require new input beyond their current approach.
Absolutely.
Okay, that presents the strong conjecture 3.1 for the sharp N52 bound. Have we missed any nuances regarding the constant?
No, I think the connection to the Gaussian distribution in the most diverse case is the key intuition there. Let's look at why their current method fails to achieve this.
The next paragraph explains the limitations. For example, one of the reasons behind the Lawson theorem 1.2 is the Minkowski distance energy bound of Roche-Newton and Rudnev.
We talked about this. That theorem itself has a logarithmic loss that can't be removed because of certain geometric counterexamples, like grids of points.
It's an observation tied to the classical multiplication table phenomenon. What is that?
A quick digression. If you look at an n by n multiplication table, you might think there are n squared distinct products in it. But there aren't. There are only about n2 log n.
Because of redundancies, 64 is the same as 83.
Exactly. This kind of structural pattern in number theory leads to logarithmic losses in these kinds of geometric counting problems. And that's exactly where the net factor comes from in their proof.
So a future direction would be to find a stronger energy estimate that doesn't suffer from this logarithmic loss.
Right. They say that might be enough to get the ON52 bound, but to get the precise leading constant, they suspect completely different ideas would be required.
Okay, that explains the origin of the no loss. A stronger incidence theorem is needed to improve the technical lemma 2.7. Have we missed any nuances?
We have clarified that getting the right exponent requires better additive energy control, but getting this sharp constant probably requires a totally different, more analytic or probabilistic approach, not just better combinatorial bounds.
The last paragraph points to a completely different direction. It notes that unlike Halász's original theorem, which can prove arbitrarily strong bounds, their result seems to cap out at N52.
Right. Their MB-based method can't prove a bound stronger than that. They ask if there are strengthenings that can.
And this leads to the theoretical maximum of anticoncentration. After all, for generic A and B, the map pi sum A BPI is injective.
Meaning for a truly random, unstructured choice of A and B, every single one of the n permutations will give you a different sum.
In that case, every value that can be a sum occurs with probability exactly 1 over n factorial.
So the max probability Q is just 1n. The expression type is the theoretical minimum concentration.
The latex is frat 1.
The phonetic is 1 over n factorial.
This is what they call factorial anticoncentration, a decay rate that is astronomically faster than any polynomial.
And their final provocative thought is about how to get there. This shows that, in principle, permutation sums can exhibit even factorial anticoncentration. Such a result would have to look beyond multiplicities for quantifying additive structure, but it is unclear to us what the correct notion would be.
So their diversity metric, MB, is based only on multiplicities, how many times an element is repeated. It's not subtle enough to capture the kind of deep additive independence needed to get to factorial decay.
A completely new kind of structural parameter is needed. That's the challenge they leave for the field.
That brings the concluding remarks to a close, posing the next great challenge, finding a structural metric that drives anti-concentration down toward the factorial bound. Have we missed any nuances in this discussion?
No, I think we've emphasized that the current work, while incredibly successful, is really just the first step. It uses the simplest measure of structure multiplicity. The next frontier is quantifying higher-order additive independence in this permutation setting. #X4D. References and context.
Okay, that concludes the body of the paper. We'll just briefly run through the references as they provide the crucial context for this entire field.
Right. BBDV 26 and DNPTV 25 are contemporaneous works on the same model, with the second one being the independent result mentioned in the footnote.
ERD 45 and ERD 65 are the classical Erdős papers on the Littlewood-Offord problem, establishing the N12 bound and the N32 conjecture.
GK 15 is the Guthkatz paper on the distinct distances problem, the deep geometric result. RR 15 is the Roche-Newton and Rudnev paper that translates that geometry into the additive energy bound that this paper uses.
Hal 77 is Halász's original foundational theorem. HK24 is the paper by Hegedus and Kerley with the permutohedron question that Pulaski answered.
POH24 is Pulaski's paper with the N1 baseline theorem. and SS65 and stay80 are the two independent proofs of the optimal N32 bound for the classical problem.
Finally, the author's email addresses are listed: zach.hunter@math.ess.ch, cosmin.POHOATA@emory.edu, and zhhd@princeton.edu.
And that's the whole manuscript.
That concludes our linear progression through every sentence and reference of the source material. Have we missed any final details?
We have adhered to the unabridged protocol completely. Every formula was spoken and every section was verified. #outro.
So let's review our mission. We set out to navigate this incredibly dense mathematical paper, and I think we succeeded. We saw how they transformed this vague concept of diversity in a set of coefficients into a precise, quantifiable statistic, MB.
And that statistic, MB, was the key. It successfully bridges the gap between the simple N1 baseline from Pawlowski in low diversity cases and the remarkable N52 plus O1 bound they achieve when the coefficients are distinct. A true permutation analog of the classical Erdős-Moser result. And we saw the incredible machinery required to prove it, the deep probabilistic tricks with the auxiliary permutations to make it suitable for Halász's theorem.
And then leveraging these extremely modern, powerful results from incidence geometry to provide the structural control needed to bound the additive energy. I think the relevance for you, the listener, is really profound here. This paper is a perfect example of how subtle structural changes in your input data, in this case, moving from high multiplicity to high distinctness, can dramatically change the behavior of a random outcome.
It's a great lesson. The next time you encounter a random process, you should ask yourself, is the randomness truly independent, or is it governed by some hidden structural diversity that could be controlling everything?
And for our final provocative thought, we'll return to the author's final challenge. If MB measures diversity by multiplicity, what is the new metric that measures diversity by true additive independence? What is the key that will unlock the door to factorial anti-concentration and push the bounds all the way down to that ultimate theoretical limit of 1 over n factorial?
That is the next frontier of anti-concentration theory. A fascinating problem and one that's going to require completely new ideas.
Thank you for joining us for the deep dive. We hope this exploration has left you feeling well-informed and thoroughly intrigued. We'll see you next time. Welcome back to the deep dive. Today we're taking on what I think is one of the densest and most elegant problems in modern combinatorics and probability.
We really are. We're looking at how to measure randomness when all your random variables are, in fact, completely dependent on each other.
Which sounds like a contradiction in terms, almost.
It does. Our source material today is a paper that really gets to the heart of this. It's titled A Halász-Type Theorem for Permutation Anti-Concentration.
And our mission for this deep dive.
Our mission is to really understand how the internal structure, that specific numbers inside two sets of coefficients, dictates how spread out their randomized sum can be.
Okay, let's unpack that title immediately because it is a mouthful.
Yeah.
Starting with the first big word, anti-concentration.
Right. Anti-concentration is, well, it's pretty much exactly what it sounds like. It's the opposite of concentration.
So if I think of a concentrated random variable, I'm picturing something like a bell curve with a very, very tall, narrow peak. All the probability is piled up right around one value.
Exactly. And if something is highly anti-concentrated, that probability mass is spread out. It's flat. The goal is to find the maximum probability that our sum hits any single value.
So we're looking for the highest peak in the distribution.
We are. It's a quantity often called Q of X.
The maximum point math.
That's the one.
Yeah.
And in anti-concentration problems, you want that Q of X to be as low as possible. You want a flat, spread out distribution.
Got it. Maximum spread is the goal. Now, why permutation? What's the source of randomness here?
This is the absolute key to the whole thing. In a lot of classical probability, when you study a random sum, the randomness comes from independence.
Like flipping a coin for each term to decide if it's plus or minus 1.
Precisely. That's the famous Littlewood-Offord problem. But here are two sets of numbers. Let's call them A equals A1 through AN and B equals B1 through BN. They're fixed.
So the numbers themselves aren't random?
Not at all. The randomness comes from how we pair them up. We take a uniformly random permutation, let's call it pi, and we calculate the sum. The random variable is...
Let me guess. The sum of AI times B sub pi of I.
You got it. And because the choices are dependent, once A1 is paired with B7, Neither of them can be used again. It makes the whole analysis just dramatically harder than the independent case.
Okay, and that brings us to the last part of the title, Halász type. That name suggests a connection to some deeper classical result.
It does. Gabor-Halász's theorem is a cornerstone of this field. In the independent setting, he showed that concentration is dictated by the algebraic structure of the coefficients.
What do you mean by algebraic structure?
Essentially, how many additive relationships they satisfy. Things like, does a 1 plus a 2 equal a 3 plus a 4? If your coefficients have a lot of that kind of neat, tidy algebraic structure, the sum tends to cluster. It concentrates.
But if they're, say, a bunch of random irrational numbers?
Then they're algebraically generic, and the sum spreads out beautifully. This paper is looking for the analog of that idea, but in the permutation world.
So they're asking, what property of the sets A and B in this dependent permutation model plays the same role that additive relations played in the independent world?
That is the million-dollar question they set out to answer. And the structural measure they find is what this whole deep dive is about.
Fantastic. Before we jump in, let's quickly credit the authors.
We should. The authors are Zach Hunter from ETH Zurich, COSMIN POHOATA at Emory University, and Daniel G. ZHU from Princeton University. For completeness, their emails are also listed. Zach.Hunter at math.PR.ch, COSMIN.POHOATA at emory.edu, and ZHD at princeton.edu.
All right, let's dive into the abstract, starting with the first sentence, which sets up the problem. I'll read it. Given a set 1A $1 in real numbers and real coefficients, $1, B, ARN, consider the distribution of the sum obtained by pairing the A's with the B's according to a uniformly random permutation.
And this defines our core random variable. Let's call it Y. So using the mathematical notation, the type of expression is the core random variable. The latex is summation.
Phonetically, that's y equals the summation from I equals 1 to n of ai times b sub pi of I.
Exactly. And again, the only thing random there is pi, the permutation.
Okay, the next sentence in the abstract introduces the baseline result. It says, a recent theorem of Pawlowski shows that as soon as the coefficients are not all equal, this distribution is always spread out at scale n $1. No single value can occur with probability larger than $1 CL and 2 where CL plus $1, and this bound is sharp in general.
This is our starting point. Pawlowski established a universal lower bound on the spread. He basically said no matter what your sets A and B look like, as long as the B's aren't all identical, the maximum point mass, the Q of Y we talked about,
The highest peak.
is at most on the order of 1 over n, or O of 1 over n.
And the specific bound is?
Okay, so the mathematical expression type is the universal maximum probability bound. The latex is $1 tall seal and 2 are n2 air car.
And phonetically, that's 1 divided by the quantity 2 times the ceiling of n over 2 plus 1.
Right, and you can see that's roughly on the order of 1 over sen. And critically, this bound is sharp. That means there are cases where the concentration is actually that high. This is the floor. It can't get any worse than this.
Okay, that immediately raises the next question. The abstract's third sentence is, we show that stronger anti-concentration holds when the coefficients have additional diversity.
And there's the central hypothesis. Pawlowski's bound is the general worst-case scenario. The authors are saying, we think we know what causes that worst case, and if we move away from that specific structure, we should get much, much better results.
The structure being this lack of diversity.
Precisely, which leads to the next sentence. We quantify the structure of the coefficient multiset by a simple statistic depending on its multiplicity profile, and prove that the maximum point mass of the permuted sum decays polynomially faster as this statistic grows.
Okay, so they're introducing a new tool, a new measurement, this multiplicity profile.
Yes. They're going to define a number, which we'll see later. It's called M of B, that captures this idea of diversity. And they'll show that as M of D gets bigger, the concentration Q of Y gets smaller, and not just a little smaller, polynomially smaller.
And that brings us to the punchline of the abstract. In particular, when the coefficients are all distinct, we obtain a bound of no PT2 plus O1, which can be regarded as an analog of a classical theorem of Erdős and Moser.
And this is the headline result. This is a massive improvement. Going from n to the -1 all the way to n to the -5/2 is a huge polynomial leap.
Let's get the pronunciation right for that.
Sure. The expression type is the new bound for distinct coefficients. The latex is none 52 tolls plus O1.
Phonetically, that's n to the power of -5/2 plus little o of 1.
Right. And that little o of 1 just hides some slower growing subpolynomial factors like logarithms. The main decay rate is that powerful n to the -5/2.
And they compare this to Erdős and Moser. Why is that the right comparison?
Because in the classical Littlewood-Offord problem with the independent +-1 coefficients, Erdos proved a universal bound of n to the -1/2. But later, it was shown that if the coefficients you're adding up are all distinct, that bound improves to n to the -3/2.
So in both cases, adding the structural condition of all coefficients are distinct gives you a huge polynomial improvement.
Exactly. It's the same philosophical leap, but in this much more complex permutation setting.
Okay, let's unpack this. That covers the entire abstract. Have we missed any nuances in the initial statement of the problem or the core claims?
I think we've thoroughly unpacked it. The key takeaways are Pawlowski sets the n to the -1 baseline, the authors introduce a new structural measure, m of b, and the payoff is that incredible n to the -5/2 bound when diversity is maxed out. Let's proceed to the introduction, section 1.
All right. The very first paragraph of the introduction immediately reframes the problem. It shifts from probability to geometry.
It does. It's a really helpful way to visualize what's going on. They define a set of points S in n-dimensional space. These points are just all the possible permutations of the coordinates of our set A.
So it's n factorial points, forming a kind of cloud in n-dimensional space.
Exactly. And the probabilistic question, when does our random sum equal some value x, becomes a geometric question.
Which is?
The equation for the sum is just the equation of a hyperplane. So the question becomes, how many of those n factorial points in our cloud S lie on any given hyperplane?
The probability is just that count divided by n factorial.
Precisely. Now there's one hyperplane we have to exclude, which they call the trivial one.
Right. The paper reads, the question is trivial if one considers the hyperplane $HE defined by $6 plus C dots plus XNCA.
Let's break that down. The expression type is the definition of the trivial hyperplane H0. The latex is $H by 1 by 1 math mid by 1 plus C dots plus XN sumid A of 4 down.
And phonetically, the hyperplane H0 is the set of points x1 through xn in Rn, such that x1 plus ... plus xn is equal to the summation over all A in A of A.
And why is it trivial? Well, if you just sum up the coordinates of a point, permuting them doesn't change the sum.
Of course. So all n factorial points lie on this one hyperplane. That corresponds to a probability of 1. We have to ignore it.
We have to. So the real question is about any non-trivial hyperplane. And Pawlowski's result, viewed geometrically, give the sharp bound on this. For odd n, the maximum number of points is n minus 1 factorial. For even n, it's n times n minus 2 factorial.
And if you divide those counts by n factorial, you get something that looks like 1 over n.
Which brings us right back to the 1 over n probability bound. It's the same result, just viewed through a different lens.
The paragraph then mentions a connection to something called the permutohedron and an extension to complex numbers.
Right, just for some added context, the permutohedron is simply the convex hull, sort of the geometric shape you get if you stretch a skin over all these n factorial points. So they're saying this is related to the vertices of that well-known geometric object. It's just to ground the problem in a broader mathematical context.
Okay, that covers the first paragraph of the introduction. Have we missed any nuances?
I think the key is just locking in that geometric interpretation. The problem is about counting points on a plane, and Pawlowski's result is a worst-case bound on that count for any non-trivial plane. Let's proceed to the next sentence.
The second paragraph gets right to the motivation. It says, a close examination of POH 24 shows that for 1 GEC 88, the only hyperplanes achieving equality in the above bound are of the form $B by 1 plus C dots plus BNXN equals C diller, where at least 1 occur 2 of the dollars are the same.
And this is the spark. This is the observation that drives the entire paper. The absolute worst case, the highest possible concentration, happens when the coefficient vector B that defines the hyperplane is incredibly repetitive.
So when the diversity of B is at its minimum.
At its absolute minimum, almost all the B coefficients are identical.
The paper then makes the logical leap, combined with the fact that, and so on, basically saying that this strongly suggests that if you have more diversity, you should have less concentration.
Right, and note the use of that logical conjunction. The authors are saying this isn't just a guess, it's a logical necessity. If the worst case is caused by low diversity, then increasing diversity must improve the situation.
It's the only way it can work.
It has to be. And then they make their big claim. In this note, we prove a result of this form that is optimal up to a factor of no log.
Let's clarify that note term again.
It just means subpolynomial factors, things like logarithms of n or even log n. They're saying their main result, the rate of decay they prove, is essentially the best possible. You can't improve the main power of n. You might only be able to clean up these minor logarithmic terms.
So they're claiming they've basically solved the problem up to some very small tidying up.
That's the claim, a very confident one.
That closes out the motivational paragraph. Have we missed any nuances?
I think we have the clear motivation. We know the worst case is low diversity, so the mission is to quantify that diversity and show that it directly controls the improvement over the 1/n baseline.
Oh.
Let's define the new structural metrics, starting with the probabilistic restatement of Pulaski.
Okay, paragraph 3 is short and sweet. It formally defines the maximum point mass. It says, let Qx, Px equals Hn.
Just the formal notation for what we've been discussing. The supremum, or sub, just means the least upper bound over all possible values of x. It's the height of the tallest peak in our probability distribution.
And then it restates Pulaski's result as theorem 1.1.
Right. It just says that for our random sum y, q of y is bounded by that 1/2 ceiling of n/2 plus 1 formula.
And crucially, it re-emphasizes the condition that the BI coefficients must not all be the same.
Of course. If they were all the same, say all equal to 1, the sum would just be the sum of the AIs, which is a constant. The probability would be 1. A totally trivial case. So you need at least 2 different B's to get any randomness at all.
That completes the definition of Q of X and the formal statement of Pulaski's theorem 1.1. Have we missed any nuances?
I think everything is set. We have the baseline theorem, we have the motivation, and now we're ready to see the new structure they introduced that allows them to improve on this bound.
And this happens in paragraph 4. This is where they define their key metrics. It starts with a multiplicity profile. It reads, let UL be the partition of nuthers corresponding to the multiplicities of the distinct elements in the multiset $.
Okay, let's break this down with an example. It's much easier to see that way. Let's say n is 8, and our multiset B is 5, 5, 2, 2, 9, 9, 9.
So we have 3 distinct elements, 5, 2, and 9. That means L, the number of distinct elements, is 3.
Right. Now we count them. There are 3 5s, 2 2s, and 3 9s. The multiplicities are 3, 2, and 3. The definition says we have to sort these in descending order.
So the 2 3s come first, then the 2. The multiplicity profile, mu of B, would be the pupil, 3, 3, 2.
Exactly. Mu1 is 3, mu2 is 3, and mu3 is 2. It's just a compact way of describing the repetition structure of the multiset.
Simple enough. Now for the main event. They define their new statistic, m of B. I'll read the formula. We additionally define 1 ella y hn nu we.
Okay, let's apply the WEDUHY mandate here. This formula looks a little strange at first, but every part of it is there for a very specific reason.
Let's start with the weighting factor, I minus 1 squared.
This is the heart of it. Let's look at what happens for the first few values of I. When I equals 1, we're talking about mu1, the largest multiplicity, the count of the most frequent element.
1 minus 1 squared is 0. So the most frequent element contributes nothing.
It contributes absolutely 0 to m of B. This is a brilliant design choice. Remember the Pulaski worst case, the highest concentration was caused by having a huge mu1.
So they've designed a metric that is completely blind to the thing that causes the worst case behavior.
Exactly. M of B is a measure of the diversity contributed only by the second most frequent element and onward. It's a measure of the diversity in the tail of the distribution of multiplicities.
And why the square? Why I minus 1 squared?
The quadratic weighting heavily penalizes multisets that are top-heavy. For I equals 2, the second multiplicity mu2 gets a weight of 1. For I equals 3, mu3 gets a weight of 4. For I equals 4, it gets a weight of 9. It gives disproportionately large weight to having many different, less frequent elements.
So a multiset with a long, flat tail of multiplicities will have a very large m of B.
A very large m of B. As we'll see, this specific quadratic form is not arbitrary. It's deeply connected to the variance of a related random variable.
Let's get the formal pronunciation for the TTS.
Sure. The expression type is the coefficient diversity statistic m of B. The latex is 1b, sum I, 1, 2, mu.
And the phonetic is m of B is the summation from I equals 1 to L of the quantity I minus 1 squared times mu I.
A simple formula, but a very powerful idea.
Here's where it gets really interesting. We've defined the crucial diversity metric, m of B. Have we missed any nuances about its interpretation?
I think the primary nuance is just to reiterate that connection to the trivial case. M of B equals 0 if and only if there's only one distinct element, meaning L is 1.
Which means all the BI are identical.
Which is exactly the trivial case that Pulaski's theorem excludes. So a positive M of B is the quantitative measure of being in a non-trivial situation. Let's look at the result this metric enables.
This brings us to the main event, theorem 1.2. I'll read the statement. It says, let A be a set of n real numbers, and B be a multiset of n real numbers with m of B greater than 0. Then we have our bound.
Okay, let's state the bound formally. The expression type is the main anti-concentration bound from theorem 1.2.
The latex is Q sum O1 N1
Phonetically, that's the concentration function Q of the permuted sum is bounded by 1 over the quantity n to the power of 1 minus little o of 1 times the square root of m of B.
This formula just beautifully connects everything. The concentration is inversely proportional to the square root of their diversity metric.
It's fantastic. And the paper immediately points out this is an analog to the classical results of Erdős-Moser, Sarkozy-Semeretti, and Stanley.
We touched on this before, the idea that adding a structural condition gives a polynomial improvement.
Right. In the classical Littlewood-Offord problem, the baseline bound was n to the minus 1/2. When you added the condition that the coefficients were all distinct, Sarkozy, Semeretti, and Stanley proved it improved to n to the minus 3/2.
A full power of n improvement.
A full power of n. Here, we're getting an even bigger jump, from n to the minus 1 to potentially n to the minus 5/2. It's the same spirit. Structure beats randomness.
Okay, let's do the calculation they mentioned in the next sentence. The fully distinct regime, or all the B's are different.
So if B is a set of n distinct numbers, what does its multiplicity profile look like?
Well, there are n distinct elements, so L is n, and each one appears exactly once, so every mu I is just 1.
Perfect. So we plug that into the formula for m of B. It's the sum from I equals 1 to n of I minus 1 squared times 1.
Which is just 0 squared plus 1 squared plus 2 squared all the way up to n minus 1 squared.
And that's a famous sum from calculus. The sum of the first k squares is roughly k cubed over 3. So here the sum up to n1 is roughly n1 cubed over 3, which is on the order of n cubed.
So for a fully diverse set, m of B is approximately n cubed.
Exactly. Now we plug m of B equals n cubed back into the theorem's bound. The denominator is n to the 1 times the square root of n cubed.
The square root of n cubed is n to the power of 3/2.
Right. So we have n to the 1 times n to the 3/2. You add the exponents. 1 plus 3/2 is 5/2.
And there it is. The bound becomes 1 over n to the 5/2.
Up to that little o of 1 factor. So this recovers their headline result perfectly.
The paragraph also notes that the estimate is consistent with Pawlowski's n to the minus 1 bound in highly repetitive regimes.
Of course it has to be. If B is, say, n minus 1 copies of a number and one other number, m of B is just 1 squared times 1, which is a constant. So if m of B is a constant, the bound from the theorem is just 1 over n. It smoothly connects back to the baseline.
A quick note, they include a footnote here acknowledging independent simultaneous work by Du, Nguyen, Fan, Tran, and Vu.
Yes, very common in fast-moving fields of mathematics. Two groups arriving at similar ideas at the same time. It's good practice to acknowledge that.
Okay, let's unpack this. We've covered the main result and its connection to classical bounds. Have we missed any nuances?
I think we really understand the core now. We see how the m of B metric interpolates perfectly between the 1 over n baseline and the powerful 5/2 bound. And we see that this 5/2 rate is contingent on m of B being near its maximum of roughly n cubed. Now we can move to the generalization where A can also have repeated elements.
Right, this is theorem 1.3. The setup is now that both A and B are multisets.
This is the more general and also more complicated situation.
The theorem states that if a certain condition is met, then we get a bound. And the bound depends on the geometric mean of the two diversity measures, m of A and m of B.
But that condition is a very strong one. Let's state it. The expression type is the required diversity threshold for theorem 1.3.
The latex is MELI-MB n3 plus epsilon.
And phonetically, m of A times m of B is greater than or equal to n to the power of 3 plus epsilon for some small positive epsilon.
That's a very high bar. Since m of A is at most about n cubed, this essentially requires m of B to be at least some power of n. You need significant diversity in both sets.
You do. And if that high bar is met, then you get a strong anti-concentration bound. Let's state the bound.
The expression type is the resulting anti-concentration bound. The latex is Q sum N12, N2 scores RT.
Phonetically, the concentration function Q is bounded by, with a constant depending on epsilon, n to the 1/2 times the quantity log n squared, divided by the square root of the product m of A times m of B.
The paper makes a point of saying this is an unusual statement. The bound is either relatively strong or it just doesn't apply at all because of that high threshold.
It's an all-or-nothing kind of theorem. If you have enough joint diversity, we can tell you something powerful. If you don't, our methods don't apply, and you have to fall back on something else, like Pawlowski's bound.
Okay, let's unpack this. Theorem 1.3 requires high overall diversity, m of A times m of B. Have we missed any nuances?
I think the main question it raises, which they immediately address, is why that n to the 3 plus epsilon threshold is necessary. It seems so specific.
It does, and the next paragraph is all about tightness, and a counterexample that shows why you need it.
Right. They start by calculating the variance of the random sum. They show that the variance is approximately m of A times m of B divided by n.
Okay, so the variance is directly proportional to this product of diversity metrics.
Yes, and this is where the intuition comes from. Low variance implies high concentration. If the sum doesn't vary much, it must be clustered around its mean.
And using a standard tool like Chebyshev's inequality, you can turn a variance estimate into a concentration bound.
Exactly. And doing so gives you a general lower bound on the concentration. Let's state it. The expression type is the general lower bound on the concentration function.
The latex is Q sum I1 A B. Phonetically, the concentration function Q is bounded below by n to the 1/2 divided by the square root of m of A times m of B.
Now wait a minute. That lower bound looks a lot like the upper bound from theorem 1.3.
It does. They match up to logarithmic factors. This tells us that their main result in theorem 1.3 is basically sharp. The dependence on the square root of m of A times m of B is the correct one.
But it still doesn't explain the threshold.
It doesn't. For that, we need their killer counterexample. It's really clever.
Okay, walk us through the setup.
They construct two multisets, A and B. Let's get the structure right. A consists of about n over 2 distinct non-zero numbers, say the integers from 1 up to n over 2 plus about n over 2 zeros.
So A has a lot of zeros, but also a lot of distinct elements. Right. It's kind of half diverse, half concentrated. And B is the opposite. It's extremely non-diverse. It consists of just 1, 1, and n-1 zeros.
Let's calculate the diversity metrics for these. For A, it has roughly n over 2 distinct elements, so its m of A will be on the order of n cubed. It's highly diverse by this measure.
It is. But for B, it has n-1 copies of 0, which is the most frequent element, and just 1 copy of 1. So mu1 is n-1, and mu2 is 1.
So m of B is just 2 minus 1 squared times mu2, which is 1 squared times 1. M of B is just 1.
Exactly. So what's the product? M of A times M of B.
It's roughly n cubed times 1. So m of A, m of B is on the order of n cubed. It's right at the edge of their threshold.
It's the critical case.
Yeah.
Now let's think about the random sum. We're summing AI times BP of I. But the B vector only has one non-zero entry, the single one.
So every term in the sum is 0, except for one, the term where some AI gets paired with that single one.
In which AI gets paired with it?
A completely random one, a uniform pick from the multiset A.
So the entire complicated random sum collapses. The random variable Y is just a single uniformly random draw from the multiset A.
And our multiset A contains roughly n over 2 zeros.
Right. So what's the probability that our random sum Y equals 0?
It's the probability of picking a 0 from A, which is about n over 2 divided by n. It's 1/2.
1/2. The concentration Q of Y is at least 1/2, a constant. That is massive concentration. It completely violates the bound from theorem 1.3.
So the theorem fails spectacularly right at the threshold of n cubed.
Which proves that the threshold can't be n cubed. It has to be strictly greater, hence the n to the 3 plus epsilon.
So what does this all mean? We've proven the necessity of the high diversity threshold via a zero-rich counterexample. Have we missed any nuances?
I think the key takeaway is that the method breaks down when one of the sets, even if the other is diverse, is structured in such a way, like having tons of zeros, that it effectively cancels out the randomness from the other set. The high joint diversity is needed to prevent this kind of catastrophic collapse. Let's finish the introduction.
The final paragraph of the intro discusses the key ingredient for the proof, which we've alluded to. It mentions a Minkowski distance energy result of Roche, Newton, and Rudnev, which itself relies on the deep incidence theorem of Guth and Katz.
And this is where we leave the world of pure combinatorics and enter the realm of deep algebraic and geometric methods. The Guth-Katz theorem was a landmark result from around 2015 that solved the long-standing distinct distances problem posed by Erdős.
What's the distinct distances problem?
It's a simple question. If you have endpoints in the plane, what's the minimum number of distinct distances between pairs of them? Guth and Katz used incredibly powerful tools from algebraic geometry to get a nearly optimal answer.
And the tools they developed can be adapted to other problems.
They've been adapted to dozens of problems in additive combinatorics and number theory. They provide incredibly strong bounds on what are called incidence problems. How many times can a set of points lie on a set of curves or surfaces? This distance energy result is one of those powerful consequences.
Okay, the introduction finishes up with some notation. It's mandatory we cover it.
Right? They define bracket n as the set of integers from 1 to n. Then they define two symbols for inequalities.
First, there's the one that looks like a less than or equal to sign with a squiggly line.
Right. The expression type is the notation for is bounded by. The latex is a less ml. Phonetically, that's just is bounded by. It means less than or equal to, up to some absolute constant. F is less m g, means F is less than c times g.
And the other is a double squiggly line.
The expression type is the notation for is approximately equal to. The low-text is approximately equal to. Phonetically is approximately equal to. This means the two quantities are within a constant factor of each other.
And finally, they define Q of x given y.
Yes, the conditional concentration. This is a key technical tool. The formula QX let EY QXY dollar lets you bound the total concentration by averaging over the concentration conditioned on some other random variable y. It's a way of breaking a hard problem down into smaller, more manageable pieces.
Lastly, there are the acknowledgments.
Yes, they thank Noga Alan for helpful comments and acknowledge support from the NSF.
And that wraps up the entire introduction. We are now heading into section 2, proofs. We'll start with the probabilistic preliminaries.
Let's do it. These are the tools they need to handle the randomness.
Continued.
Welcome back to the deep dive. Today we are entering a zone where pure randomness seems to meet this deep inherent structure.
Right.
Imagine you have two lists of numbers. Let's call them list A and list B. You know exactly what's in both.
Okay.
Now, what happens if you randomly shuffle one of those lists and then multiply and sum up the pairs? What happens to all the possible sums you could get?
Do they all clump together around one value?
Exactly. Or do they spread out so much that, hitting any single value is incredibly unlikely? This simple thought experiment is really the engine behind a huge amount of modern probability and combinatorics.
And that tension you mentioned between the randomness from the shuffle and the structure that's already baked into the lists themselves, that's precisely what we're going to explore today.
And we are going deep.
Very deep. This is a highly specialized dive requested by one of our learners, and it focuses on a major result in additive number theory. The paper is called a Halász-type theorem for permutation anticoncentration.
So our mission today is to give you the ultimate conceptual shortcut. We are not just summarizing, we're going to perform what we call an unabridged protocol.
Line by line.
We're going to dissect this paper with extreme granularity, explaining the core definitions, the logical flow, and some of the surprising conceptual leaps that, unlock this incredibly complex machinery.
The hope is that this will give you a really profound understanding of how modern mathematicians quantify concepts like spread and diversity.
So the core problem, if we state it simply, is about bounding the probability that one of these random sums hits a specific single target value. Let's call it X.
And the intuition is, the more diverse your original sets A and B are, the harder it should be for the sum to concentrate on any one value. This means the distribution becomes strongly, anti-concentrated.
Let's start right at the top then with the title itself. A Halász-type theorem for permutation anticoncentration. There's a lot packed in there.
Oh, absolutely. The title is a dense signpost. It tells you exactly what intellectual tradition this paper belongs to.
So that first part, Halász-type. What does that signal to a mathematician?
It immediately connects this work to the seminal efforts of Gábor Halász back in the 1970s. Halász basically revolutionized the study of concentration functions.
How so?
He brought in these incredibly sophisticated Fourier analysis techniques. These are methods designed to probe the deep, hidden additive structure of number sets. So by claiming Halász type, the authors are telling you we are using high-powered analytic tools for this combinatorial problem.
Okay, so that sets the method. Then the word permutation. This defines the source of randomness.
Exactly. And this is a critical distinction from, the classical random sum problems. The randomness here comes specifically from permuting the coefficients of B against the variables of A.
Which means the random parts are dependent on each other.
Yes.
Yeah.
If you pick one pairing, it affects all the other possible pairings. This is totally different from the classical Littlewood-Offord model, where randomness comes from independent coin flips. That dependency creates a whole new set of mathematical challenges.
And the last piece, anti-concentration. As we said, this just means we're focused on how spread out things are.
We're focused on the maximum point mass. We want to find an upper bound for Q of x, which is the maximum probability that our random sum x equals any single value. We want that probability to be as small as possible.
And we should definitely acknowledge the authors here.
Yep.
This is a collaboration across some major institutions. Zach Hunter from ETH Zurich, COSMIN POHOATA from Emory, and Daniel G. Zhu from Princeton.
Which really reflects how cross-disciplinary this kind of work has become.
Okay, I think that really sets the stage. Let's do our first completeness check. That covers the title and authors. Have we missed any foundational context or, rhetorical purpose in that initial framing?
I think we've thoroughly unpacked it. The title's implications are clear. The scholarly context is set. I think we can proceed immediately to the abstract.
All right, the abstract. This is our conceptual roadmap. The very first sentence just establishes the problem setup.
It says, given a set A, A1, and of real numbers and real coefficients, B1, Bn, consider the distribution of the sum obtained by pairing the A's with the B's according to a uniformly random permutation.
So very formally, A is our set of values, B is our multi-set of coefficients.
Right, and the sum, which we'll call x, is determined by a random permutation, which we'll call pi. So the random sum x is just the sum from I equals 1 to n of a sub I times b sub p a.
Okay, that's the setup. Let's do a check. Have we defined the key elements from that first sentence clearly?
We have, and that setup is absolutely essential for everything that follows. Let's move to the next sentence, which introduces the existing work.
The second sentence immediately gives us the baseline result, which is crucial for context. It says, a recent theorem of Pawlowski shows that as soon as the coefficients are not all equal, this distribution is always spread out at scale n to the minus 1.
So this is the universal floor. This is the worst case anti-concentration you can expect in this permutation model. As long as you introduce any diversity at all into the coefficients, as long as they're not all identical, Pawlowski showed that the maximum probability mass, Q of x, is at most on the order of 1 over n.
And the paper gives the exact bound. It says, no single value can occur with probability larger than 1 over 2 times the ceiling of n over 2 plus 1, and this bound is sharp in general.
Let's break that down because it's important. So we're looking at the expression for the anti-concentration bound. The latex is frac1 LCL n2 urcil plus 1.
And to read that out phonetically.
The fraction 1 over 2 times the ceiling of n over 2 plus 1.
So for a large n, the ceiling of n over 2 it's basically just n over 2.
Exactly. So the denominator is roughly 2 times n over 2, which is n plus 1. So the whole thing is on the order of 1 over n. It's an O of 1 over n scale.
And that's what you'd sort of expect if you just had n equally likely outcomes.
Precisely. Pawlowski's result proves that the randomness of the permutation, even with coefficients that are almost identical, guarantees a spread that's at least as good as if you had n uniform outcomes. It's the minimum expectation.
All right, completeness check. That covers the existing baseline result by Pawlowski. Have we explained the significance of that n to the minus 1 scale?
Yes, I think so. The n to the minus 1 scale is the universal floor. Anything better than that requires more structure. Let's move to the author's new hypothesis.
And here we get to the core thesis of this paper in sentence 3. We show that stronger anticoncentration holds when the coefficients have additional diversity.
This is it. This is the fundamental claim. If the coefficients in your multiset B have some interesting structure, if they are highly diverse, then Q of x should drop much, much faster than 1 over n.
So this moves the problem from just finding a worst-case bound to actually quantifying the benefit you get from having structural complexity.
Right. Completeness check on that sentence. It was a brief statement, but have we highlighted its importance as the central thesis?
Yes, I think so. The thesis is crystal clear. More diversity implies stronger anticoncentration. Now we need to see how they quantify that diversity.
Which brings us to sentence 4. We quantify the structure of the coefficient multiset by a simple statistic depending on its multiplicity profile and prove that the maximum point mass of the permuted sum decays polynomially faster as the statistic grows.
Okay, so this is where they signal the introduction of their new metric, which they'll later call M of B. It captures this idea of a multiplicity profile.
And that claim of polynomially faster decay is mathematically huge. If 1 over n is linear decay, polynomially faster means it decays like n to the power of negative c, where c is bigger than 1.
That's a huge qualitative difference in the kind of randomness being generated.
A massive difference.
Okay, completeness check. That covers the quantification of structure and the general nature of the improved result. Any terminology we've missed?
Not yet. The specific definition of the M of B statistic is still to come, so I think we can move on to the most improved case they mention.
And sentence 5 delivers the punchline. This is the best case result. In particular, when the coefficients are all distinct, we obtain a bound of n to the power of -5 halves plus little o of 1.
Let's just pause and appreciate that jump. We are moving from a universal floor of n to the -1 to a structural bound of n to the -2.5.
That's an enormous difference.
It's a huge leap. It means that the simple fact that the coefficients are all distinct is driving this incredibly powerful increase in the dispersal of the final sum.
And what about that little o of 1 term, the n to the o of 1?
That just means the exponent is -2.5 up to a factor that grows slower than any polynomial. It's typically a logarithmic factor, a log n term somewhere, which they'll discuss later. It's a very small price to pay.
And the sentence ends, which can be regarded as an analog of a classical theorem of Erdős and Moser.
And this is vital for context. It situates the problem. Erdős and Moser got a similarly huge improvement in the classical Littlewood-Offord problem when they assumed the coefficients were distinct. It shows that structure in the inputs translates directly to stronger anti-concentration in the output, no matter which random model you're using.
So the abstract has really given us the entire arc. The universal floor, the tool they use, and the high diversity ceiling.
A perfect match.
Completeness check. That concludes the abstract, highlighting the main bound and its historical significance.
Is there anything else we need from the abstract before we hit section 1?
No, I think we're ready. Let's dive into the introduction for the formal definitions and theorems.
All right, section 1, introduction. It starts by reframing the whole problem geometrically.
Right. Paragraph 1, sentence 1, let A equals A1, A cli n is a set of n real numbers, and let S be the set of points, where pi ranges over all permutations of n, 1 to n. So instead of thinking about sums, we're now thinking about all the possible vectors in n-dimensional space that you can form by just shuffling the coordinates of x.
This shifts our perspective completely. The permutation sum, the sum of A times BPI equals some value C, is now geometrically equivalent to asking how many of these points in our big set S lie on the hyperplane that's defined by the coefficients by.
The text then immediately points out that the most basic hyperplane, which they call H0, actually contains all of S.
It says, as stated, this question is trivial, as every point in S lies in H0 x0 equals by 1x n and Rn, such that by 1 plus xn equals the sum of A and A of A.
We have to pause on H0. What is this thing?
It's the hyperplane defined by the sum of the coordinates being a constant. And since just permuting coordinates never changes their sum, all n factorial possible permutations of A must lie on this one hyperplane. It's the constant sum hyperplane.
Let's do the formal reading for our listeners. The expression type here is the hyperplane equation H0. The latex is H0 less by 1 plus C dots plus xn plus xna in ma.
And the phonetic transcription is, the set H0 is the set of vectors x sub 1 through x sub n in R to the n, such that the sum of x sub I from I equals 1 to n is equal to the sum over all elements A in the set A of A.
This is the trivial case, right? The concentration here is 100%.
Exactly. The problem is only interesting when it's not trivial.
Okay, completeness check. That defines the geometric setting and the trivial sum hyperplane H0. Have we explained why this geometric framing is equivalent to the permutation sum problem?
I think so. We've established the basis. A sum equaling a constant is the same as finding points on a hyperplane. So let's proceed to the non-trivial case.
Paragraph 2, which discusses Pawlowski's result for any hyperplane that isn't H0.
Right. Sentence 1. If we exclude H0, this question was recently answered by Pawlowski, who showed that the maximum number of points in S lying on a non-H0 hyperplane is n1 if n is odd and n times n2 if n is even.
So Pawlowski solved the geometric problem completely for any non-trivial hyperplane. The total number of points in S is n factorial, assuming A has distinct elements.
And for a large, even n times n2 factorial is just n factorial divided by n1. So it's a fraction of the total points that's very close to 1 over n. This is the geometric version of that O of 1 over n bound we saw in the abstract.
And then comes this stunning connection in sentence 2.
In the case A inner OR, this result can be interpreted as bounding the maximum number of vertices of a permutohedron that can lie on a hyperplane.
Let's define the permutohedron.
So when A is the set of integers from 1 to n, the set of points S is all the permutations of the vector 1 to n. The permutohedron is the convex hull of these n factorial points. It's this really complex, beautiful geometric shape that's central to combinatorics.
So Pawlowski's result is literally about how many corners of this specific shape you can slice off with a single flat surface.
Exactly. It grounds this abstract probability problem in very concrete geometry, and sentence 3 just notes that this result was quickly extended to complex numbers and other fields, which shows how important it was.
Okay, completeness check 2.2. That covers the geometric interpretation of Pulaski's work and the link to the permutahedron. Did we miss any connections there?
No, the general hyperplane bound is confirmed. Now we can trace the motivation for the current paper directly back to these findings.
Paragraph 3. This is where we get to the core motivation for Hunter, POHOATA, and Zhu. The authors state that Pulaski's own analysis showed that this maximum concentration, it only happens for very specific kinds of hyperplanes.
This is the crucial leap. Pulaski found that for n greater than or equal to 8, the only hyperplanes that achieve that maximum possible concentration are defined by coefficients bi, where, quote, at least n minus 2 of the bi are the same.
In other words, the multiset B has almost no diversity. It's almost completely constant, with at most 2 distinct values.
Right, and this leads directly to their logical deduction in the next sentence. If low diversity gives you maximum concentration,
Then as the bi become more diverse, it should be possible to prove stronger upper bounds.
the whole reason for this paper springs directly from that structural observation by Pulaski. We know the worst case is driven by a lack of structure, so the best case must be driven by an abundance of it. And they claim their result is optimal up to a factor of n to the O of 1.
Completeness check 2.3. That establishes the core motivation for studying diversity in the coefficients. Have we clearly explained the link between coefficient structure and the degree of concentration?
The connection is solid. Low diversity means high concentration. Therefore, high diversity must mean low concentration. That's the problem they're tackling.
Paragraph 4 now formalizes the notation Q of X one last time before restating Pulaski's theorem as theorem 1.1.
Right. Q of X is the maximum point mass probability. And theorem 1.1 just sets that low diversity baseline. We should read it out formally.
Let's do it. The expression type is the anti-concentration bound. The latex is Q left some I, N, N, I, B, N 2 Herschel plus 1.
And the phonetic transcription is the maximum point mass probability Q of the sum from I equals 1 to n of a sub I times b sub pi vi is less than or equal to the fraction 1 over 2 times the ceiling of n over 2 plus 1.
And again, we have to emphasize that this bound holds as long as the coefficients bi are not all the same.
Critical condition. If they're all the same, the sum is constant and Q of X is 1.
Okay, completeness check 2.4. That formalizes the notation and restates the O of 1 over n result. We've emphasized the not all the same condition. Are we ready for the main definition?
We are. Paragraph 5. This is the key definition of their diversity metric. First, the multiplicity profile, mu of B.
So for a multiset B, they define its multiplicity profile, mu of B, as a partition of n into parts mu1, mu2, and so on, where mu(I) is the count of how many times the i-fifth most common element appears.
And L is the total number of distinct elements. The sequence is sorted, so mu1 is the largest. For example, if B is 1, 1, 1, 2, 2, 3, then n is 6. There are 3 distinct elements, so L is 3. The multiplicities are 3, 2, and 1. So mu of B is the partition, 3, 2, 1.
Okay, that makes sense. Now, for the derived statistic m of B, we additionally define mb, the sum from I equals 1 to L of the quantity I1 squared times me.
This is the author's really ingenious definition of diversity. We have to do the why mandate here. Why this specific formula?
Right. What's the intuition?
Notice the quadratic weighting, I minus 1 squared. For the most common element, I equals 1, the weight is 0. This means the count of the most common element, mu1, contributes absolutely nothing to the diversity score m of B.
Which is perfectly logical. The most common element is the least random or least diverse part of the set.
Precisely. The second most common element, where I equals 2, contributes 1 squared times mu2. The third, where I equals 3, contributes 2 squared, or 4 times mu3. This design aggressively quantifies how far the multiset B is from being, monochromatic.
So if B has no diversity at all, L is 1, and m of B is just 0.
And if B have maximum diversity, all distinct elements, then L is n, every mu I is 1, and m of B becomes the sum of I1 squared from I equals 1 to n. That sum is on the order of n cubed.
So m of B is this diversity lever ranging from 0 to O of n cubed. Let's do the formal reading. The expression type is the diversity statistic m of B. The latex is MB, sum I1, 2.
And phonetically, that's the statistic m of B is the sum from I equals 1 to little l of the quantity I minus 1 squared times mu sub I.
All right, completeness check 2.5. That formalizes the central diversity metric M of B. Have we thoroughly explained how it quantifies diversity?
Yes, we've established it measures diversity, ranging from 0 for no diversity to O of n cubed for maximum diversity. Let's move to the main theorem.
Theorem 1.2. This is where we see how that lever works. Let A and B be a set and a multiset, such that M be 0, then Q of the sum is less than or equal to 1 over n to the power of 1 minus little o of 1 times the square root of M of B.
This is the central outcome. Notice the M of B term is in the denominator. So as diversity increases, M of B grows and the overall bound gets smaller, meaning anti-concentration gets stronger.
So let's check the max decay case. If M of B is at its max, roughly n cubed,
then the denominator is roughly n to the 1 times the square root of n cubed, which is n to the 3 halves. So n to the 1 times n to the 3 halves is n to the 5 halves, and 1 over that is n to the minus 5 halves. It perfectly recovers the bound from the abstract.
Let's read out the formal bound from Theorem 1.2. The expression type is the main anti-concentration bound. The lect text is the Q left sum I1 right, and the phonetic transcription. The maximum point mass probability Q of the sum is bounded by the fraction 1 over n to the power of 1 minus little o of 1 times the square root of M of B. Completeness check 2.6. That details Theorem 1.2, showing the direct relationship between diversity M of B and the strength of anti-concentration. Any remaining ambiguities?
No, the relationship is explicit. Now we can place this result in the larger historical context.
Paragraph 6 does exactly that, contextualizing this within the Littlewood-Offord legacy.
Right, so the classical Littlewood-Offord, or LO problem, asks about the concentration of a sum, let's call it x, which is the sum from I equals 1 to n of a sub I times x psi sub I, where the psi sub I are independent random variables, like coin flips.
And Ergus, back in 1945, proved that the sharp universal bound for this independent model as Q of x is bounded by n to the minus 1/2.
That's the universal floor for the independent model, and notice the baseline exponent is different. It's minus 1/2 for independent sums versus minus 1 for our dependent permutation sums. The permutation model is inherently a bit more spread out.
Then came the structural dependence. Erdős and Moser later proved that if the coefficients, the AI, are all distinct, the bound improves dramatically.
It jumps from n to the minus 1/2 to n to the minus 3 halves plus little o of 1.
This is the perfect analog. The exponent jumps by a full unit in both cases, from minus 1/2 to minus 3 halves in the independent model, and from minus 1 to minus 5 halves in our permutation model. Distinctness buys you an entire power of n.
Right, and as the paper mentions, Sarkozy, Simoretti, and Stanley later managed to remove that little o of 1 factor in the classical case, which immediately sets up the big open problem for the permutation model.
And the final piece of historical context is Halász himself.
Halász showed that in that classical model, concentration is controlled not just by distinctness, but by the number of short-signed additive relations among the coefficients, something called additive energy. Our current paper is Halász type because it's trying to quantify that same underlying additive structure, but for the permutation model using their M of B statistic.
Okay, completeness check 2.7. That concludes the historical analogy with the classical Littlewood-Offord problem and Halász's framework. Have we successfully positioned Theorem 1.2 as the permutation analog?
Yes, the parallel is very clear. Pawlowski's n to the minus 1 is like Erdős's n to the minus 1/2, and Theorem 1.2's improvement is the analog of the n to the minus 3 halves improvements, just in this different setting.
Paragraph 7 then just reiterates this, confirming that when M of B is small, the bound goes back to Pawlowski's floor, and when M of B is big, it hits their ceiling.
It's all consistent. Then we proceed to Theorem 1.3, which is an extension. It allows A to also be a multiset. Before, A had to be a set of distinct elements.
Right, so now both A and B can have repetitions, and both have their own diversity metric, M of A and M of B.
And Theorem 1.3 states, let A and B be multisets such that MA and B is greater than or equal to n to the power of 3 plus epsilon for some epsilon 0. Then Q of the sum is bounded by a constant times n to the 1/2 times log n squared over the square root of MA.
This is a lot more complex. Now the anti-concentration is governed by the product of the diversities.
And that log factor, the source of the little o of 1, is now explicitly visible. But the most crucial part is that condition. The theorem is conditional. It only holds if the product M of A times M of B is very large, exceeding n to the power of 3 plus epsilon.
And the authors themselves comment on this in paragraph 9, calling it an unusual statement that the bound is either relatively strong or non-existent. If the total diversity is low, the theorem says nothing.
Exactly. Let's do the formal reading for Theorem 1.3. The expression type is the multiset anti-concentration bound. The latex is Q left sum IAM A, B, NCN AM2.
And phonetically.
The maximum point mass probability Q of the sum is bounded by C sub epsilon times the fraction n to the power of 1/2 times the square of the natural logarithm of n over the square root of the product m of A times m of B.
Okay, completeness check 2.9. That covers the statement of theorem 1.3, emphasizing the product measure of diversity in that epsilon constraint.
Yep.
So what are the consequences of that condition?
Well, the authors immediately comment on it, and then in the next paragraph, they justify it by proving tightness.
Right, paragraph 10. They demonstrate the tightness of the bounds. They start by calculating the variance of the permuted sum in a model case.
And the result is that the variance is approximately m of A times m of B, all divided by n. The expression type is the variance of the permuted sum, latex. The variance of the sum from I equals 1 to n of a sub I times b sub pi of I is approximately m of A times m of B divided by n.
Intuitively, this makes sense. The spread, the variance, is proportional to the total diversity of the part.
Exactly. Then, using Chebyshev's inequality and the pigeonhole principle, they derive a lower bound on the concentration.
The result is a lower bound on Q. The expression type is the lower bound on concentration. Latex Q left sim frasum I A am phonetically. The maximum point mass probability Q of the sum is bounded below by the fraction n to the power of 1/2 over the square root of the product m of A times m of B.
And this lower bound is structurally almost identical to their upper bound in theorem 1.3. They're separated only by constants and that log n factor. This proves the near optimality of their result.
But they still have to justify that strong condition, m of A times m of B being greater than n to the 3 plus epsilon. They do this with a counterexample.
This is the definitive test. They construct a very specific pair of multisets. A has very high diversity, m of A is about n cubed, but B has very low diversity, m of B is just 1.
So the product m of A times m of B is on the order of n cubed, which just fails to meet that n to the 3 plus epsilon threshold.
Right, and in this specific case, the permutation sum simplifies to just one element of A, chosen at random. And since they constructed A to contain at least n over 2 zeros,
The probability that the sum is 0 is at least 1/2.
a maximum concentration Q of X of at least 1/2 is massive. It's not anti-concentrated at all. This one example proves that the n to the 3 plus epsilon condition isn't arbitrary. It's necessary to guarantee there's enough structure for the strong bound to actually hold.
Okay, completeness check 2.9. That covers the tightness of the bound and the necessity of the strong diversity condition in theorem 1.3. What's the final framing before we get to the proofs?
Just a quick note on the proof method and a formal definition of notation.
Paragraph 11 names the core strategy. It says, an important ingredient is a Minkowski distance energy result of Roche-Newton and Rudnev, which in turn relies on a deep incidence theorem for points and lines in R cubed due to Guff and Katz.
And this is a critical piece of framing. It tells us that this problem, which started in probability and combinatorics, is ultimately solved using these extremely high-powered results from a field called incidence geometry.
Which is all about how geometric objects like points and lines intersect.
Exactly. And this reliance on geometry is where both the power and ultimately the subtle weakness, that little of one factor of the proof, lies.
After a quick notation section and acknowledgments, that's the end of the introduction.
Yes.
Completeness check 2.11. That completes section 1, the introduction, including all formal definitions, theorems, background, and notation. Have we maintained strict linearity?
We have. We've proceeded strictly through the introduction. We are now prepared to dive into the mathematical mechanics of the proofs in section 2.